Правильные микрофоны, которые...
Микрофон вот этот, он уже... Есть два микрофона. Раз. Статическое электричество, осторожно. Причем ядреный очень разряд. Губами не прикасаться.
У нас Telegram есть?
Нет, с Надеждой у меня есть, я ей пишу. А вот с Кириллом
нет, не Кириллу я сказал. Сейчас позвоню.
Так, Надежда я написал.
We are waiting for organizers of this conference, Professor Andrei Terehov and deputy from High School of Economics. So they asked us to make it 3 minutes for waiting time. Hello, everybody. We could start. I have the honor to open our 16th Spring Summer Symposium on Software Engineering in Voronezh. Many thanks to all participants of this event, because during our not simple, turbulent times, it was not simple for everybody. of course, many thanks to all organizers, program committee and organizing committee. And I took a remark, especially participation of some foreign members of program committee. They're working in our team as usual. And I think we could start. We should not spend time for not interesting things, but now Sergey Lebedev could congratulate you with this, our opening. Sergey, you are ready?
Yeah, I'm ready. Hello.
Sure, you're welcome.
Thank you. Hello, dear participants. Many thanks to invite me on your conference, on your summer software engineering colloquium. I think these 2 days, what you would work on it takes many different interesting results of your research work, and it will be the best time to spend in communication after 2 years of isolation. I wish you a good work and spend a nice time in Colloquium. Thank you. Good luck.
Okay, thank you. Sergey, do you have connection with our invited speaker, Nadezhda? So let's wait a minute. So about format of our event. When we started, we decided to use only English during all days of our event. It was quite reasonable because maybe not many, but few foreign participants were involved in our activity during this period. But right now, it seems all participants, at least now, have good Russian too, and maybe not very good English. So some relax of this format. We continue use English everywhere is possible, but if somebody asks in Russian, speaker can't answer in Russian too. So if you ask in English, please explain your ideas in English too. So we follow language of participants of our events. Oh, really? Okay. So now I can present first invite a speaker, Nadezhda Chirkova. She's a research fellow of Center of Deep Learning and Bayesian Methods of High School University. Your topic of your talk very interesting for us. So it's not only some advanced techniques in deep learning, but this attempts to apply these techniques for analysis and maybe correction of software. So it's not only talk about new technologies, but about new application of this technology exactly in software engineering. So Nadezhda, are you ready?
Yes, hi.
Yeah. Hello.
Thank you very much. Let me share my screen. One moment. No, not this one. Sorry. Second try. I guess now it should work. So can you see it on the large screen? I hope so.
Yes, we can.
Okay. Yes, hello everyone. My name is Nadezhda Chirokova. I'm a research fellow at the HEC University at the Center of Deep Learning and Bayesian Methods of the HEC University. And today I will give a talk on neural source code processing with transformers. So the general goal of the talk is to give the overview of the modern state of neural source code processing field. So we'll briefly talk about applications, talk a lot about approaches. So how can we build these applications, and also touch upon open problems of the field. I won't dive into too many technical details as we have limited time, and I don't think it will be very useful. Instead, I will focus on the main concepts of the approaches that we'll talk about. I won't rely on too many knowledge of machine learning, and I will recap everything we need in the presentation. But generally, I assume that the audience is familiar with like main idea of machine learning, like what is learning, for example, and things like that. And of course, I will not cover all works in the field. Instead, I will just focus on the main works. And also, I included some of my works in this presentation as my main research field is actually deep learning for source code, applying neural networks for source code processing. So let's begin. About questions, do you usually write questions during talk or after talk? I guess it's after talk, yeah? So should I follow chat or not? Okay, let's just go through the presentation and we will find it out during presentation. Okay, so as you maybe already know, that deep learning is now widely used for source code processing, and it's not like only in academic papers and conferences, but also in real-world applications. So, for example, there are good neural network-based solutions for code generation, bug detection and repair, automated documentation, and they are usually implemented as, for example, plugins for IDEs. But of course, deep learning is not like a pile for everything. It has its area of usage. And deep learning is used for the tasks that we cannot solve with static analysis or with rule-based approaches, but that for these tasks, we have a lot of data. We have collected a lot of data and we can use it to build our solutions. And so what are example tasks that we can solve using this deep learning approach? This is, for example, code completion, when we need to predict next tokens, bug detection and repair, where we, for example, here we need to locate the variable that is used wrongly and locate a variable which can be used to repair this bug. Function naming, where we are given a body of the function and we need to predict function name. Code translation, where we can translate from one language to another, or code generation, where we are given a textual description of the code we want, and the neural network will generate us this code. The code snippet that does what we want. So in all these tasks, we can collect training data, and we can build solutions using this training data. Actually, neural network achieve quite good results in these tasks nowadays. Of course, not perfect results, but actually very impressive. So for example, you maybe heard about the Codex model, which was released last year, which is able of generating code of really high quality, syntactically correct, and the code that corresponds to your intent. So for example, here we need to return the sum of all odd elements of the list in even positions, and the network generates this code for us, and the code is actually correct. Okay, so these were the example of applications where we can use deep learning. Of course, it's not all tasks. I just gave you some examples so that we know what tasks we are talking about. And now let's move on to how can we build these systems? How can we use neural networks and why neural networks for these tasks? And let's begin with reminding about general machine learning paradigm. So in machine learning, we are given a large set of training data, which we use to automatically build our algorithm. So it's not like we think how a person would solve this task and program it. No, we use training data to automatically infer this algorithm. And then we have some new data for which we want to make a prediction, and the algorithm will return this prediction for us. So for example, if it is a task of code generation, the training data will be a set of pairs of textual description and code, a lot of these pairs, not tens of them, like hundreds of thousands ideally. And then new data will be a new textual description, and algorithm will generate us a new code snippet. It will be our prediction. And so, of course, the problem with that, we need this data. It's not very trivial in a lot of tasks. In some tasks, it may be, we already have data, but in some tasks, not. So as I already said, for example, for code generation, we need hundreds of thousands of textual description code pairs. And where can we take them? It may be a problem. And often there are three scenarios for obtaining this data. First is automatic parsing from GitHub. So for example, we can parse functions with their docstrings. The problem with that, this data will be quite noisy. So there will be a lot of bugs in this, like errors in this data. Another approach may be to use synthetic data. It won't work for code generation, but it will work. It may work, for example, for bug detection. So we can take code without bug, inject synthetic bug there, and it will be our training data. And the third way is human labeling. But it is very expensive. So if we need a human who will label for us hundreds of thousands of training data, it will be quite expensive and take up much time. So I think the main approach to take the data in source code processing is actually parse it from GitHub in some way. Okay, so let's assume we have our training data. Now we want to build an algorithm. Here we usually need to decide on three questions: how we preprocess our data, which neural architecture we use, and how do we train this neural network. And as for the first question, data processing, source code is usually represented in one of three ways for neural networks. So the first approach is just textual representation, plain textual representation. The second approach is parsing syntactic tree from our code, and the most commonly used is abstract syntax tree. I think you are all familiar with it. And also a popular representation is a graph representation. For example, data flow graph or control flow graph. I also think you are all familiar with that. So usually code is represented as one of these types for processing with neural networks. Okay, now we need to decide what model to use. And the first question, why actually neural networks? There are other machine learning algorithms, for example, decision trees or linear models. Maybe you heard of them. But these classic approaches, they usually work well for like simple tabular data. When we have a table, like a set of features for each object, for each instance. But in tasks where we have more complex data, like structured data, these classic algorithms like decision trees usually don't work well. And for tasks with structured data, we usually use neural networks. And the reason is that we can build specific neural networks, neural architecture, it's called, for different types of data. And in case of source code, it's also the case. So we can build different, we can actually consider different architectures for processing code. And here are some examples. So for example, for code represented as graph, we can use specific graph neural networks. For code represented as a sequence, we can use, for example, recurrent neural networks. So recurrent neural network is a very popular architecture which processes sequences. And here, each next, so there is a concept of state, and each next state is computed based on the previous state. So here it's the recurrence, why it's called recurrent, like next state based on previous state, and so on. There are also, for example, recursive neural networks, which are based on the similar concept, but for trees. So here we have a tree, and each parent state is computed based on children's states. Again, as I said, I will just give brief descriptions, like general concepts, so we won't dive into too much detail here. And also there are transformers. About transformers, we will talk a little bit more. So there are different neural architectures which we could use for source code. And actually in the literature, there are papers that consider all these networks. However, some of them perform better, some of them perform worse because of some technical issues. And nowadays, two most popular architectures for source code are graph neural networks and transformers. And transformers are actually more widely used. But graph neural networks may perform on par with transformer or even a little bit better in some tasks. For example, in bug detection and repair, graph neural networks are quite widely used. Recurrent and recursive neural networks, they usually perform worse than transformers, for example. So they usually they were used in earlier works, but recent works usually don't use them. Okay, so in this talk, we will focus on transformer as it is most popular solution now, and we will talk about details of transformer on the next slides. And the third thing is training scheme. How will we train this network? And the most popular approach is just classic training, where we train our neural network given some inputs to predict some outputs. For example, in code generation, we train our neural network given a textual description, it needs to output our code snippet, which follows this textual description. And we have these pairs in training the data, and we just train our neural network to predict code given text. But there are some more complicated schemes. We will touch upon some of them later in the presentation. So this was like an overview of the system. How would we build it? We decided that we will use transformer in this presentation. We will also talk how can we pass different types of data, like the ISTs, graphs, to transformer. Transformer can process different types of them. And also we'll talk about training scheme, two training scheme actually, first and second. Okay, so there are no questions in the chat. Okay, I think we'll answer questions at the end of the presentation. And what time is it? Okay, so the transformer has quite a lot of technical details, but again, and all these details are needed to enable it working, performing well. But again, we will focus just on its core mechanism, which is called self-attention mechanism. Let's talk briefly about it. So let's first think that our code is represented as in a textual representation, as a sequence of tokens. For example, diff, add, bracelet, x, and so on. In transformer, we will have several layers. They are denoted in different colors here. And at each layer, we have a vector for each token. So these are, for example, vectors for our 4 tokens. And it will continue for a longer sequence. And each layer updates these vectors. So given old set of vectors, it returns new set of vectors. And the main idea in transformer is that all vectors are connected to all vectors. So for example, when we want to update the vector of token add, we will use all vectors of all other tokens. And what these vectors mean, they encode the meaning of this token in some way that is known only for neural network. Okay, so we use all vectors to update all vectors. So for example, here also it depends on all other vectors. And this is in contrast, for example, to recurrent neural networks. So in recurrent neural network, each vector is updated based on the previous vector. So for example, add would be updated based on diff, bracket will be updated based on add, x based on bracket, and so on. And it will have this recurrence. And it may perform not very well because of this recurrence. And in transformer, everything is connected to everything. And at each layer, we have this update procedure, and after several layers, we have our final vectors. Okay, but let's do it with a little bit with some formulas. So how is it implemented? Let's denote input of the layer as x's, output vectors as z. And here, for example, like zi is computed as the weighted sum of all x's with weights alpha ig. And the main thing is how we obtain these weights. So these weights are computed based on vector similarities. Let's look here. So each weight, how each token contributes to G's token, is computed based on vectors xi, xj, and like their scalar product. So we take the scalar product, it's just a normalization constant, don't pay much attention to it. And we have this like pre-weights. And then we compute our final weights using some normalization scheme. It's called softmax, but it doesn't matter. So the goal of this normalization is that we will have weights that are all non-negative and sum to 1. And after that, we plug these weights to our formula. So basically, each z is just a weighted combination of input x's. And it happens at each layer. Again, in transformers, there are a lot of other different technical things. We just won't touch upon them. It's out of the scope of this talk. Okay, and also there are 2 parts of transformer, encoder and decoder. So encoder is used to process given code. So we have the whole code snippet. For example, in bug fixing, we have our code snippet. And we just apply the scheme that we discussed on the previous slide. And it is called encoder. And decoder is used when we want to generate new sequences. So for example, here it's represented for textual description, but it may be also applied to code. So we generated token by token. So for example, first we generate word adds, then a, then number, then 2, and so on. And as at each time step, we only have the currently generated sequence. We don't have future tokens. We cannot use this all-to-all self-attention. So here we use attention that looks only on previous tokens. So when generating A, we look at start and at adds. When generating number, we look at starts, adds, A, and so on. Okay, but basically the decoder is organized in the same way as encoder. It's just this modification with masking future connections. And also we can have encoder-decoder system. For example, given the text, given the code, we want to generate text. And in this case, the decoder will not look only on previously generated tokens, but it will also look at all code. For example, when generating adds, it will look at start and at all input code. When generating A, it will look at start, adds, and all code, and so on. And we will have this encoder-decoder architecture. Okay, so this was general idea of transformer. It's called a global architecture, as all tokens are connected to all tokens. And now let's discuss how can we process code with this transformer. So actually, as I mentioned before, we can pass code in different ways, like in abstract syntax tree, as a graph. All these forms can be processed with transformer. But let's begin with the most simple way of treating code as a sequence of tokens. Diff, like count lines, bracket, file name, and so on. The problem with the scheme that I already described for you is that it's now invariant to the order of the input elements. So let's return to this formula. So here we discuss that Z is a weighted sum of all X's. And as the summation procedure operation, it's invariant to the order of the elements. If we reorder all tokens, the output won't change. So here we do not utilize the sequential order in any way. And that's the problem. And to fix it, a technique called positional encoding is usually used. It's a very simple technique. It says that at the first layer, we basically have these vectors for each token, blue ones. And we will also have vectors that encode position. So vector for 1, vector for 2, for 3, for 4, and so on. And we will sum them. Like here. So the first vector encodes information about code token, and the second encodes information about position. We will just sum them up. And it actually works quite well. And in natural language processing, and this is the field for which the transformer was initially developed, in natural language processing, this positional encoding is used in a lot of tasks and applications. So this is the first way. How can we, so this is needed so that we incorporate sequential order in our transformer. Positional encoding. Another way how can we do that is relative attention. It's called relative attention. So here are again formulas of self-attention. We saw them on the previous slides. And here the main idea is that we will incorporate information about relative positions in this self-attention. So we will add these vectors that encode these relations inside self-attention. For example, when we compute this green vector, we will think that, or this green vector, we will think that this vector is one token right from this vector, one token left from this token, and 2 tokens left from this left token. So these are relative positions, and information about them is encoded inside self-attention. Okay, actually, these were all formulas that we will have in this presentation. On the next slides, we will only have images and illustrations. Okay, so we have transformer. It utilizes the sequential structure of our input, and we can use it on different tasks that we discussed on the first slide. And for example, this work by Kim et al., they used it for code completion. So for example, given the beginning, their system needs to generate next tokens. And actually this team, they develop a real world like plugin that for code completion. So this is not just an academic paper. They have also a product with this system. And so they report that if we represent code as sequence, transformer performs, for example, much better than RNN. So they have transformer and recurrent neural network. And this number, this is like mean reciprocal rank. Let's not dive into what it means. It's like a metric for code completion. If it's 100%, then the token is always on the first position, the correct token. If it's 0, then it's a very bad system. And here we have like 50%. It's quite good result. So transformer performs much better than RNN. And also in this paper, they have transformer that processes abstract syntax tree. We will talk about it on next slides. And let's just briefly look at the results. So the transformer that processes trees performs a bit better than transformer that processes sequence. Here we have 55%, here we have 58%. And also it works better than other solutions that are developed specifically for processing code, like based on decision trees or on attention. And here are some examples. So in type-based system, it's like very simple baseline. The needed token is placed at the top of the suggestion. So it's not what we want. The recurrent neural network places it at the second position and transformer places it on the first position. That's actually what we want from the system in this particular case. It's like just an illustration of the system. Okay. So now, as I promised before, let's discuss how can we utilize syntactic structure in transformer. So let's assume we have some code snippet. Here I have a very short code snippet, for example. We can use arbitrary code here. We parse its abstract syntax tree. So we have a type in each node, which represents the syntactic unit like a sign or subscript float. And in some nodes, we also have values that store variable names, function names, AP names, and so on. So how can we process this IST with transformer? Basically, we again have, we have nodes. For these nodes, we will have vectors, as we discussed before. It won't be a problem. So in each node, we will have a vector of the type and vector of the value. That's okay. But the problem is that we need to utilize the structure of the tree. And what we can do now, we can process sequential. What we already know is how to process sequential structure. So the first option would be just to use the depth first traversal of our abstract syntax tree, for example. So we obtain this traversal. Traversal will be a sequence. And for this sequence, we can use techniques we discussed before, positional encoding or relative attention. And here I append word sequential because we will now have these techniques for trees as well. So the first option is just to obtain a sequence from the tree and use known techniques. But some papers, some work to go further and generalize these techniques for trees. So for example, the work of Shiv et al., they developed tree positional encoding. It's the same system, the same scheme as we discussed before, that we add a vector of token, a vector of token and vector of position. But positions are now considered in the tree, not in the sequence. And how can we encode positions in the tree? We can just, for example, encode the path from the root to our node. For example, go to the second child, first child. We'll have these positions and their vectors will be summed with the vectors of tokens. It's called tree positional encodings. Yeah. And also we can propose a similar approach to this relative attention, but for trees again, tree relative attention. Again, we will incorporate information about relative positions in self-attention in transformer and how are relative positions encoded in trees. So for example, we have one node, another node, and we want their relative position. How is it encoded? It could be a path from one node to another, for example, up, down, down. So we can build this table of these pairwise roots and utilize them in self-attention. That's what this work does. And also there are other approaches, for example, Gigin and sandwich. What is this model? So here we will combine two models. the model that processes graph and the model and transformer. So our model will consist of alternating layers of transformer and layers of graph neural networks that we mentioned on first slides. And we will just need to obtain a graph from our tree. We can tree actually is a graph, but we can add some additional edges if you want. Okay, so as we see, there are different ways. Again, it's just general concepts. We don't dive into details. How can we process trees in transformer? These different techniques were proposed for different tasks and tested on different data sets. So we had our research group had a question: what is the best approach? What should we use in practice from these approaches? And in our paper on empirical study of transformers for source code, we compared these techniques on 4 tasks. So we consider variable misuse, function naming, and code completion. We consider 2 languages, Python and JavaScript, and compare these 5 approaches that I just described. And what we observe is that for variable misuse, degenerate sandwich and sequential relative attention perform best. And degenerate sandwich was actually developed for this task, for variable misuse task. In function naming, they all perform similarly, except for the easiest positional encoding scheme. In code completion, we predict values and types. And when we predict values, sequential relative attention performs best, orange line. And when we predict types, this tree relative attention performs best. So when we incorporate this technique, when we incorporate information about relative roots in transformer. So actually, the main result of our paper is that this sequential relative attention performs best in 3 out of 4 tasks. And interestingly, this technique was not considered as a baseline in previous works. So we showed that it actually, this is a technique from natural language processing, and it usually outperforms techniques developed specifically for source code. And we suggest to use it in future works. And we also compare these techniques in terms of time and memory requirements, and we show that it's also much more efficient. It's faster and requires less memory. Okay, I suggest that we skip a couple of slides. This one. Okay. This was about our other paper. Let's skip the slides as we don't have time for them. I should finish in 15 minutes, I guess. Okay. So we discussed that we have this transformer. We can process sequences, trees, and even graphs with this transformer. If we alternate, for example, graph layers and transformer layers. So this was about architecture. And as already said, transformers are now, they usually outperform other architectures. But there is still, in our presentation, there is still room for improvement, how we can build even better solutions. So we have now a fixed algorithm transformer, but we can modify, build more complex training pipeline. So this was what we had before. We had training data, build algorithm, and use it on prediction stage. But what is usually used now and what performs better is this scheme in which we use pre-training and fine-tuning, so 2 stages. I will tell what it means now. I just want to note that it often happens in neural source code processing that techniques are borrowed from the natural language processing, because natural language processing is this big field in which very great results were achieved in recent years. And as source code, as the data domain is close to natural text, it usually borrows some solutions. And these solutions from NLP, they may really outperform solutions developed specifically for code. So we just saw this on the previous slide when we saw that sequential relative attention technique borrowed from NLP outperformed in a lot of tasks. It outperformed techniques developed specifically for code. And here it will happen again. So we borrow the scheme, the pipeline from NLP, and it will outperform models developed specifically for code. So what does it mean pre-training and fine-tuning? It means training in 2 stages. So the first stage is called pre-training, in which we have really large corpora of pre-training data, and we train some general model. This model usually in this scenario, it won't be able to solve our particular task. It will be general model. It won't, because we don't have task-specific data here. But this model, it will know code specifics, like it will know code syntax, like the different concepts like data flow, contraflow, and so on. It will learn automatically from data, from large corpora, like the whole GitHub, the entire GitHub. And then starting from this general model and having small task data, because for our task, we usually don't have very large corpora. We will obtain our task-specific model. And this second stage is called fine-tuning. So this was pre-training, this was fine-tuning. And after that, we will use this task-specific model to obtain prediction on our new data. So how is it usually implemented in this pre-training? In this scheme, the source code is usually represented just as a sequence of tokens. No abstract syntax tree, no graph structure is utilized. And this is because it's actually not needed. So during this pre-training stage, the algorithm automatically learns all of these things from the data, and incorporating, for example, syntactic structure in transformer, as we discussed before, it won't increase our performance because it is not needed when we work with such large data set. So we have our code just as a sequence of tokens. We apply some pre-processing to it. Usually it's pre-processed using this technique called sublocal segmentation. We split complex identifiers into parts. And it is done so that each token, each part will have some relatively high frequency in the data set. So because some complex identifiers that may be very rare, by using this segmentation, we will ensure that all tokens are frequent in the data set. But the problem will be that some identifiers will be split into several parts. So we will now have several tokens that represent one identifier. But it appears that it's okay for these models. They automatically learn that these are all parts of one identifier. So we have this sequence. Then how do we do this pre-training? It's usually done using mask. It's called masked language modeling. Let's just see an example. So we mask some tokens in this code randomly. For example, here, 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 and here. We just erase our token and replace it with mask. Then we pass this code to the transformer and ask it to restore these masked tokens. So the transformer needs to predict that this mask corresponds to list, this mask corresponds to bracket, this mask for and this for range. And during this procedure, this masked training, the transformer learns actually this that code is structured, that follows syntactic rules of the language and so on. It's when it happens on the very large corpora, this mask training, it's enough for the model to learn all code specifics automatically. And for example, here are example results of this model is called CodeBERT, example model. BERT is a name of this pre-trained transformer from NLP, and here it's called CodeBERT because it's trained for code. So here are 6 languages, and the task is code documentation. So given code of the function, the network needs to predict the description for this code, textual description. And the metric is below. Again, it's some metric that measures the quality of the generated text. Again, 100% is ideal prediction, 0% is very bad prediction. And these numbers, about 20, I cannot say they're very, very good, but like it's not random prediction. It's quite informative prediction. And here CodeBERT is compared to recurrent neural networks, transformers, and also this BERT, but pre-trained not on code, but on text. And we obtained that compared to plain transformer, this is transformer without pre-training, and this is transformer with pre-training. And we obtained that compared to transformer without pre-training, we obtain higher, much higher numbers. So CodeBERT really performs better in this task. And let's see an example. So here we have this function, create or update, self, list ID, subscriber hash, and data. And the goal description is add or update a list member. CodeBERT generates create or update a list member. RNN, for example, generates creates or updates an email address, not relevant at all. And transformer generates create or update a subscription. It's again less relevant than a list member. But there are again, so what we use now, we borrowed technique from NLP used for code and obtained that it achieves much higher results in our task. But again, we can utilize code specifics to adapt these techniques for code processing and achieve even better results. And it's also done in the literature. Yeah, I wanted to say that as an example, I give here a task of code documentation, but this increase in performance in these papers, it was shown in papers about this pre-training scheme. It was shown for other tasks as well, code generation and so on, bug fixing. This pre-training stage appears to be useful in all tasks. So as I said, we can improve this scheme using code specific. For example, we can propose code specific pre-training. So this was this scheme with masks, as that I described before. And in this paper by Baptiste Razier, they propose pre-training that utilizes code specific. Actually, they use variable naming objective. So they say that let's like anonymize all variables in source code and ask our neural network to name them. It will be our auxiliary task used for pre-training, and they show that it improves performance. Or for example, our paper, in our paper, we consider different ways how can we do this sublocal segmentation. And show that if we utilize code specifics, we can either increase performance or remain performance on the same level, but speed up prediction. So for example, we show that we can use these composite punctuation tokens, and it will reduce our lengths significantly without quality drop. I'm starting to go quickly through slides because we don't have much time left. So the several last slides. So we had first scheme when we just trained our neural network. Then we had second scheme, pre-training and fine-tuning, which is actually state-of-the-art approach now. But one more step, this codex model, it uses even, it shows that an even simpler scheme could be used. So in Codex, they again use pre-training, pre-train this general model, and they pre-train a really large model, much larger than all previous models on really large data. And they show that in this case, we actually may not need the fine-tuning stage. We can just formulate our new task as as a prompt, and this model will solve it, will be able to solve it even without fine-tuning. So they use pre-training. And then, for example, when you want to generate code, they just write it as a beginning of our code. So for example, we want to generate code that generates the sum of all odd elements in the list that are in even positions. We say like def solution, we want now a function. We write down what we want in textual description and comment. And we just ask this codex network pre-trained on a large corpora just to continue this code. So we just formulate our task at the beginning of the code snippet and ask it to be continued. And network generates needed code. Again, this works if we have really large network and large data. For example, here they try different model sizes and show that. So this is the portion of tasks for which all tests were passed by the generated solution. Let's look at this first column. So if you use small model, only 2% of tasks are solved. And if you use really large model, about 30% of tasks are solved, much larger number. And K, it means how many functions, how many solutions can be generated and try. So if we try just one function, we can solve 30% of tasks. But if we can try 100 samples, 100 generated codes, we will have 70% solutions, much higher. What I wanted to say that this human-eval data set, so the tasks in this data set, they are not very complex. So a typical example was shown here. So these are not like competitive programming tasks, but not very easy. So it's like middle complexity of the task. This model was also tested on much more complicated data set, and of course the numbers were lower. Okay, so we discussed approaches, general ideas. How can we use neural networks, transformers to process code, to develop solutions? But of course, we cannot say that this field has stopped in this development. No, there are a lot of open problems. So first, the code that generated by these systems, we cannot guarantee that this is correct, fully correct. There may be errors. There are a lot of errors actually. They could be obvious, but they also could be hidden. So the generated code may look correct, but it won't pass all tests, for example. So we shouldn't over rely on this system and on these systems, and we should improve them further in this direction. There are, of course, security problems that the generated code may be vulnerable. There are data security problems that models pre-trained on large corpora, they usually remember like code from training data, and they may generate this code. But this code may be prohibited by some restrictive license, and it will be some problem. Another problem is that all these models that were discussed on the last slides, they are usually quite large and slow. And it may be not very easy to use them online in production, like on the fly. It may be quite slow. We need to speed them up and to make them smaller. But when we make them smaller, they start performing worse. So this is a room for improvement. And also an actively studied research direction now is how can we utilize the project context. So usually in practice, we don't have just one function or one code file, we have the whole project, and we want the model to utilize all project structure, like classes architecture, a piece from different libraries, library versions, and so on. And how to utilize it in deep learning models is now an actively studied direction. So to sum up, we discussed transformers. It's like neural network architecture that was initially developed for text processing, but it's often it's used successfully used in for other domains as well, including source code. And surprisingly, it outperforms models developed specifically for code. We discussed that we can use transformers. We can modify them to utilize code specifics. but we can also pre-train them using just general approach for pre-training, and it will usually outperform task-specific models. And this Codex model that was released last year by OpenAI, it's capable of generating long executable code. It's quite impressive, but of course, it's not an ideal system, and this field will continue developing in coming years. So thank you very much for your attention. I guess I did my best to be on time, but it took several more minutes than I expected. So if you have any questions, please ask them. We can discuss something in more detail.
Thanks a lot. What about questions to our speaker?
Thank you very much for your presentation. And I want to ask if you use some verification methods to test the correctness of the code that is generated by different machine learning algorithms.
The existing works, they usually use, so works on code generation, they use unit tests. So they have the testing dataset consists of description of the code we want to generate, and it comes with some tests, unit tests, and they are run on the generated code. The number of tests and how well they cover the solution depends on the dataset, on the application. There are works that consider like only 3 tests. There are works that consider much more tests. It depends on the goal of the work. I guess it also depends on where you want to use. So if you want, so these academic works, their goal now is just to show that the code could be generated because before it was not it was not possible. But of course, if you're talking about applications with high security risks, for example, we need to cover it better with tests. As for some specific verification methods, I don't know works that consider something more complicated than just unit tests. So maybe it's a good direction for future research.
Yeah, thank you very much.
I'm especially interested in part of your talk when you speak about trees. The main part of your talk was about strings, but part about trees was, I have an impression that actually you reduce the problem of trees to the problem of strings. So for example, as you say, depth-first search. Is it correct? My impression is not specific to tree techniques, but reduction. And why I'm especially asked this question, because I'm interested in applying machine learning to program analysis and transformation, which is already done on abstract syntax trees or even program graphs. And if I would try to apply the methods there, then I would like to specific tree-oriented methods. Could you tell us a bit more about this?
Mm-hmm. Here, as I said, the one solution would be just to use traversal and use sequential methods. But these other techniques, they considered directly trees. So they proposed techniques similar to positional encoding or relative attention, but for trees. So these techniques, they process trees, not strings. My general message, particularly on this slide, was that in our research, we found that on tasks that we considered, using these tree-specific approaches may be not effective compared to just sequential sequential approaches. So here we found that surprisingly for us as well, sequential relative attention outperforms these tree-specific solutions. But of course, it depends on the task, and you should try different approaches if you think that processing trees is really important in your application. but I will suggest trying all these approaches. We have released our code, so you can maybe use it in your research as well. But there are also other works that were released after our work that also propose some other approaches for processing trees in transformers, and not only in transformers. So you can, of course, you can try these approaches for trees. I hope I answered your question. Not sure. Maybe you ask one more question, if not.
Yes, I have one more question. Do you consider different programming languages and examples separately from each other, or maybe it has sense to consider them together in some combinations, something like that?
I'm sorry, them of whom?
Do you consider different programming languages completely separately from each other, or maybe it has sense to leverage some information that was studied for one programming language for another one?
Okay, yeah, now I get it. Thank you. So when we in these pre-training based approaches, all languages are usually considered together. So one model is pre-trained for different languages, and then in fine-tuning stage we can use also different languages. This is because these are large models; they have enough capacity to learn all languages simultaneously. In these models, that utilize ASTs, usually these models are much smaller. They have less capacity, so usually one programming language is considered. But I guess depending on the size, if we take, for example, a bit larger network, we can try to combine the different languages, and it should perform as well. Yeah, it should work as well. So we can combine languages in one model.
So thank you. So I have like a question. Maybe it's not like very scientific, but it's more like about practice. So imagine we have a library of some ready-to-go smart contracts for blockchain. So these are just some programs that run on the blockchain, and also like we have some data sets of typical implementations of different types of smart contracts, for example, NFT tokens. So how do you like evaluate that such code generation tools are close to business application, where we can just specify some characteristics of the desired smart contract, and like the neural network will be able to generate them?
I guess the question how to evaluate, it's not like a question for me, because if it's how to correctly organize evaluation, I think this is usually a question for the person who formulates the task. Maybe so I don't know what to comment more on that. Here, what my talk was about, that we can generate some code, for example, or solve other tasks. We have output of our neural network. What happens next with this output? How is it tested, evaluated? It's like second stage. It was not covered in my talk, and I guess it's task specific and more should be specified by the person who considers the task. So I don't know what to comment on the evaluation stage. Sorry.
Thank you for the talk. The question is, do I understand correctly that a neural network can generate syntactically incorrect code also?
Yes, it's possible. Yeah, it may happen. In this, if you're talking about pre-trained models, they most often generate syntactically correct code. but not 100% cases. If we're talking about these models that are like, for example, tree-based, there are, for example, approaches that generate code, like generate abstract syntax tree to guarantee syntactic correctness. But even in that case, it may be it may be may contain errors unless we, in our grammar, we take into account all possible errors. So yeah, it may happen that it generates syntactically incorrect code or wrong code. Yeah, so no guarantee that it will perform 100%.
Does approach with encoding AST is better in this sense than approach which takes code in general without syntax tree?
Yeah, I guess it's better. And also there are recent works that combine both worlds. So they generate code in textual manner, but they filter out during generation, they filter out syntactically incorrect tokens. So they guarantee a generation stage, let's try to guarantee using this grammar that generated code is better. Yeah, so I guess it's a better approach. Mm-hmm.
And other approaches to encode not only abstract syntax tree, but also context rules like semantics in compiler. So like a definition of variable, like every variable should be defined and so on. Can we encode this?
So other restrictions, not only syntactic, but
not only syntactic, yes, but semantics, which are usually compiler.
I don't know works that do it now, especially for pre-trained models. So I guess it may be interesting again for future direction, but the problem would be how you test it. So these works that try to guarantee syntactic correctness during generation that I mentioned, so the problem, it's easier to think of it, but the problem is that it be maybe really slow. We need to parse partial trees very quickly, and they do it. So you will need to test your additional properties also really fast. It may be some technical issue. But what I wanted also to say that generally the network tries to generate code that is like close to code from the training data, from training data distribution. So if in training data we had correct code, it will try to generate correct code as well. But again, as we discussed before, not in 100 cases, and we can propose some additional techniques to ensure that all properties are satisfied. And that was the first part of my answer. Yeah.
And can we, one more question if possible?
Of course, of course.
Can we say something about stability of this network? So how taking a simple modification of input can give us a wrong answer?
There are studies that show that if we, for example, rename some variable in the input or do something like that, like semantically preserving transformation, the output of the network often can change. It is an open problem here. But if, for example, during training, we use some data augmentations, then it will solve this issue. But again, data augmentations are like specific, for example, variable renaming. But if we come with another semantic preserving transformation, it won't be covered again by this model. So yeah, this may be a problem that the output of the network is not stable when we make some changes to the input. But it is a general problem of machine learning. It is being researched actively now, but it may happen. Yeah, it's a problem.
Okay, thank you.
I'm not sure we have
silence, and it seems Vadim asked my question. So it seems no questions now. Okay, thanks a lot again. Very interesting and promising topics of your research.
Thank you for the invitation and for very interesting questions.
Thank you.
Okay, thank you. Okay, so next moderator.
both presenters are both presenters here. Who is the first presenter? Vladislav, Miroshnikov. Please. Your presentation is with, you will bring your computer. Now I articulate some while you're switching on. So we have time schedule, 15 minutes for talk. Vladislav, also keep in mind, 15 minutes is for your talk. And when you see red figures, then it is already time for questions and for closing. 20 minutes means not 20 minutes for talk because we lose time. So it is some reserve and also some time to switch presenters, lecturers. So we shall not follow precisely wall clock. So I will measure your precise by this timer when you are ready. So please, okay. I'll announce. Vladislav Miroshnikov will present Diff tool for comparing .NET assemblies in the Rider IDE. Please.
Okay, hello everybody, good afternoon. I'm Miroshnikov Vladislav and I'm a third-year student at St. Petersburg State University, Mathematics and Mechanics faculty, Department of Software Engineering. And so today we are talking about Diff tool for comparing .NET assemblies in the Rider IDE. So let's look at introduction. .NET platform is a Microsoft platforms and which is very popular in nowadays and in demand among developers. However, there are two versions of .NET platforms from Microsoft, .NET Framework, which supports only Windows operating systems, and it makes .NET Framework obsolete and not really very relevant these days. And there is also a .NET Core, now renamed to .NET 5 or 6, which is already cross-platform and it meets with modern industry standards. And in .NET platform, there is such a key concept as assembly. It is a collection of types and resources assembled to work together and form a logical functional unit. And so .NET developers from time to time wants to see the difference between two compiled assemblies, for example, when updating a third-party libraries in their project, but existing solutions don't provide the needed functionality, or for example, don't support .NET Core or have some other drawbacks. So it is proposed to implement assembly diff tool and add it to the Rider IDE, take into account existing drawbacks of existing solutions and improve comparison capabilities. So now let's look at different types and contents of .NET assembly. In .NET platform, there are the following types. We have executable assembly. Usually it is file with extension .exe on your disk. And assembly is presented as a dynamic link library file .dll, and there are also divisions into single file and multi-file assemblies. And depending from .NET platform, it means .NET Framework or .NET Core, there are also own subtypes of these types of assemblies. And I just note that all existing types of assemblies should be supported in assembly diff tool. And if we talk about structure of assembly, assembly consists of 4 parts. It is first assembly manifest, type metadata, IL code, and resources like JSON, XML, audio files, and etc. So I just know that the most important in structure that .NET assembly doesn't contain C# code or F# code or other .NET compatible code. It contains so-called IL code, aka bytecode, intermediate language of .NET Virtual Machine. It's something like Java bytecode. Maybe somebody see it. Let's look at existing solutions. Here we can two groups. First, you can apply any .NET decompiler, for example, ILDAS, ILSpy, or .pig from JetBrains, and next apply a text comparison tool. But such solutions are not very interesting for us. And the next group is complete solutions, for example, BDIF or just assembly, but they have own significant disadvantages. For example, BDIF doesn't support comparison of .NET 4 assemblies, and in our days, it makes this tool not very relevant. Let's talk about project. And first, it has been decomposed into 3K subtasks. First, we need to disassemble the assembly and find objects that are different and contain source code. Next, second, we should decompile found objects back to sharp code because, as I said before, in assembly, it will be no sharp code. In assembly, we can find only IL code. And the last task is calculate and display the difference to the user, presented as decompiled sharp code. Let's look at the first version that was done. It's something like a draft, first draft, or MVP, minimal value product. And IntelliJ platform already includes abilities to compare directories or archives. And in IntelliJ IDE, also possible to compare jar files. For Java, jar files is something like analog view of .NET Assembly. And this first draft version was based on the comparison of the IntelliJ platform. And here we can see a table with .NET types. And if we choose a row, we can see the compiled code for this pair of classes. But we not limited in one way how to represent the diff, and we suppose it's more correct to consider alternative option. So we now we review the Assembly Explorer subsystem. It is existing subsystem in the Rider IDE, and it provides a wide range of exploring assembly contents, and it contains 4 parts: metadata of assembly, references from other assemblies, packages, modules, resources of assembly, like such as JSON files, XML, and others. And last one, and most important, is namespaces and nested types. This subtree contains classes and with its internal parts like methods, fields, events, and so on. So after we review Assembly Explorer subsystem, we made the following key decision. We choose to implement diff between assemblies in the tree form because it will expand the comparison capabilities, because we can compare not only source code difference, but also differences in resources and references. And let's look at assembly diff tool architecture, presented as a UML component diagram. And first, we need to understand the Rider architecture. Rider consists of 2 operating processes running in parallel with open memory space. And it has a front-end process which responds for user interface, runs on Java virtual machine, and based on IntelliJ platform. And Rider also has a backend process. It is responsible for code analysis, refactorings, and other logic, and it's based on the ReSharper. And so architecture of diff tool is something like global architecture of Rider. We have also front-end components written in Java Colloquium and runs on Java virtual machine. Also, we have a backend. On backend process, we have backend components written in C# and running on .NET virtual machine. And for communicating between processes, we use protocol model, a special development protocol model, and its model uses a reactive distributed protocol. Let's talk about implementation based on assembly diff tree and about general operating principle. First, assembly diff tool works as follows. When a user requests to compare two assemblies on the front end, the front end assembly tree is initialized with additional components, and to backend is sent asynchronous backend request. So on backend, assemblies are read, and internal backend tree is initialized, which is created separately for each request. And when parsing assemblies among various meta information, we search for objects and divide it into three subtrees of references, resources, and source code of assembly types. And for each of subtree, we apply our special algorithm. And next, from backend tree, using protocol decimal model, we exchange and data to front end. And on the front end side, we calculate the difference and display to the user when a source code node is clicked on. So let's look at example. Yeah, here we can see on the left side we see assembly diff tree. Not wearing good image. Okay, we can see assembly diff tree, and in the root node we can see difference in versions of assemblies, architecture, and others. Also, we see reference node and resource node and namespaces nodes. And for example, double clicking on the main method on this, we can see the compiled code in the right side. And also navigation is done to this method. Okay, next, let's talk about algorithm of assembly diff tree construction. First, assembly diff tree is a K component, is a K constant in assembly diff tool. And first, we need to, when we on the backend side, when we get request, we load assemblies and creating the root node of the tree with version and architecture and other. And after the assemblies are loaded among various meta information and other contents, we are looking for so-called entry points, and contains first level of the tree. It will contains a reference node, resource node, and namespaces nodes. It is namespace, it is container for .NET types. And globally, on every level of the tree, we have three entities. It is nodes, presenters, and providers. And each level of the tree is built as follows. For each node, the corresponding provider is triggered, which builds the next level of the tree and spawns the children. It's possible to say that n-1th level provider creates nodes of the nth level. For example, if you work with class node, the corresponding provider for the class will spawn children of this class. It will be methods of this class, fields, events, delegates, nested class, and so on. And presenters for each node are used to create a view of this particular node. It means generating text, setting styles and colors, and others. And in general, assembly diff tree is constructed applying BFS algorithm to traverse the tree in order of levels. So let's look at individual subtrees. And first, let's look at references tree. Here, all references from old and new assembly, all left and right, will merge and grouped by name without version. And we will have two groups. One group will be with no pair. It means removed or edit reference, like this edit or remove. And second group will be old, new reference pair, like this. And for this, we will calculate the difference in versions and display it to the user. Okay, next, for resources, we do the same. We merge from old and new, grouped by name, and here, for example, we can see removed resources of assembly and edit. So let's talk about assembly type subtree algorithm. And first, algorithm is as follows. The first stage is to search for namespaces from both assemblies and group them by a unique for .NET CR qualify name. And also we, sorry, we will have two groups here. Namespaces without pair, it means added or removed, and group with old new namespace. And for this group, we apply quick and full check to determine the state node. Quick check compares number of nested types of this namespace pair. Full check compares CLR name of nested types as sets. And next, we build children for a namespace. It will be classes, interfaces, enumerations, records, and also we have two groups here with no pair and old new pair. And for second group, we apply quick check. We compare signature with this pair, and full check. If quick check fails, we apply ill-code rendering. And for other levels, we also group, merge and group by name, and also apply quick and full check. And we will have one unusual case. We will have a third group. We can appear third group. There will be tuples of 3 or more types. It can be because in .NET there is an overloaded mechanism. We can have methods in one class with the same name. And also we apply algorithm for calculating signature differences. For example, here we can see for .NET types addition of generic parameters in class or changes of return value in some field from int float. And now let's talk about last.
Quicker to conclusion.
Okay.
To reserve for questions. Either you have no time for questions.
Let's talk about algorithm of semantic comparison of .NET types. For example, suppose we have the following situation. We have in old assembly, we have two methods add with signatures, and in new also two methods, but signature changes, and implementation maybe can change, maybe not. So here is a question: how do exactly we map these methods? And for this, we introduce this algorithm. We introduce, first of all, it's algorithm for types that can be overloaded, and we introduce a metric invariant that different signatures, methods with different signatures and the same name, they are not considered different. And we introduce metric. Our metric works as follows. For the chosen pair of .NET types, we define in the proximity of these types by different checks. And for example, here's a small piece of code. For example, if first and second is static, virtual, override, or others, we increment similarity counter, and next we sort all methods, all pair entities from old and new assembly, and use a gradient algorithm, sorting pairs and finding the closest one, then the closest of remains, and so on. So, and feature of this tool, it is expands the resource comparison abilities, adds the ability to view differences in resource content, and integrate an assembly tool in .pip and FreeSharper. So thank you for your attention.
Thank you very much. We have time for questions, fortunately. Please, questions. Who want to ask a question?
Thank you for your presentation. And I want to ask, you have mentioned that .NET assemblies are very similar to .jar classes that are present in Java. So could this approach be applied to the Java different bases?
Okay, thank you for your question.
Yeah, thank you.
I suppose .NET assembly is not very similar to jar. I said that, 1 second. In the first version, in IntelliJ platform, there is also implemented Diff for jar files, and it looks like this for jar. It will be Java classes, and when we click on a row, we will see a diff in jar files. And we reuse, in the first draft version, we reuse something like this for Java to .NET and got this. But answer a question, I suppose yes. If we want to do something like that in not in Reiner but in IntelliJ IDEA, we can build the same tree for the Java and also show the diff for Java or Auto-encode for JVM assemblies, JVM jar files. And answer, yes, it can be applied.
Thank you very much. No, we have no more time for questions. It's time for for switch between presenters. Let's thank presenter. Thank you very much. Next presenter, Ivan Grigorov. While he's setting the presentation, I will announce Extensible IP core library for high-level synthesis. Ivan Grigorov. Thank you very much.
Hello, ladies and gentlemen. I would like to present you my presentation. It is called an extensible IP core library for high-level synthesis. My name is Ivan Grigorov. I work in Elbrus. Without further ado, let's begin. First, I would like to introduce you to the problem. Hardware designs are continuously increasing in complexity. The manual development of such designs is a difficult and error-prone process. Moreover, it requires the knowledge of hardware description languages and hardware design skills. Here comes the concept of high-level synthesis, or HLS for short. High-level synthesis, or HLS, is an automated design process which takes as input an algorithmic description of a program and creates the hardware design that implements the desired function. Usually, the input program comes in high-level language such as C, C++, or Python, for example. The process of HLS consists of the following steps. First, it translates an algorithmic description of the program into formal representation, usually in the form of control and data flow graph. In resource allocation, types and the number of available resources are selected to satisfy the design constraints. Then operations are scheduled into cycles. In the final step, happens binding, that is, each variable that carries values between cycles is bound to storage unit. Each function, each operation is bound to functional unit, and data transfers are bound to connection units, usually bus or multiplex. Of course, to design a complex design, you have to use subcomponents which implement some functionality. Some subcomponents usually are called IP cores, but in the past they were also called, as far as I remember, virtual components. These IP cores have to be organized in library, which will provide means to extract some information about their RTL interfaces and maybe their internal structure as well. Then you have to integrate this IP core in a single designs. However, there are some problems. Firstly, IP cores may have complex interfaces without any machine-readable semantics. Second, their implementations may be, their implementation languages may be different, and abstraction levels may be different as well. For example, RTL and TLM. So the first step to integrate IP cores is to specify information about IP in some way. The possible solutions are some form of textual representation, spreadsheets, and IP delivery standards. Of course, the only viable solution is IP delivery standard. There are a number of IP delivery standards at the moment. The most prominent of them are System RTL standard, Standard Universal Verification Methodology, or UVM for short, XLR Portable Stimulus and Test Design, or PSS for short, and IPexec standards. IPexec standard, excuse me. What can we say about the first three of them? System RTL standard was introduced to define registers and memories. It provides a wide functionality to do so, but it is has very narrow range, so to speak, to identify other types of components. UVM and PSS standards are mainly used for verification purposes, and they have similar problems. So the only viable solution is IPexec standard. It proposes a description of metadata of IP cores, including information about their interfaces in a standard way. It also supports so-called vendor extensions to describe user-defined vendor features. But the most important point is that it is industry adopted. That is, if you want to, so to speak, communicate with other IP vendors, you have to use this standard. So it is the only real choice at this moment. The next step for integration is to propose a method for IP integration in HLS process. In the proposal, in the proposed method, IP integration is done in compilation step. Excuse me, there is a typo. It takes as input IP core library with IP exact specifications and scheduled control and data flow graph, which comes from the previous step in the process of high-level synthesis. That is scheduler. And it produces an RTL model, usually in the form of HDL or Verilog model. The main steps of this method can be are presented in this picture. In the first step, the scheduled and maybe optimized control and data flow graph is used to get the so-called RTL intermediate representation. Then code generators are called, actually they may be integrated in the library. It is not necessary that they have that the picture represents the actual in the final step, the interconnection takes place. In the first step of interconnection, a query is sent to a library, which is an active component. Library passes the corresponding IP exact specification and RTL intermediate representation is updated. Now it contains RTL interfaces. Also, this step may include the generation of communication modules that provide means to connect interfaces, different types of interfaces between each other. And finally, the RTL model generation takes place, in which after which is produced either Verilog or HDL model. The implementation of this method has been done in Utopia EDA tool, which is currently being developed in ESPRAS. In this picture, we have the overall architecture of this tool. Gray color indicates parts which were changed, which have been changed to implement this method. And a test example has been introduced to test the correctness of the implementation. This test example is IDCT implementation of written on Hill language. IDCT stands for inverse discrete cosine transform, and Hill is the internal language in Utopia EDA. Also, this method takes as input IP library containing IP cores of the following operation: addition, subtraction, shift, and rounding. Also, I have to note that addition model have been implemented in VHDL and other were implemented in Verilog. The produced output has been tested with has been compared with manually written IDCT implementation. Testing has shown that this implementation has been correct, and this implementation supports code generators and supports IP cores implemented in different hardware description languages. Thank you very much for your attention.
Thank you, Raj. We're almost on time. So questions, please. Do somebody have questions? Then I'll ask a question. As I know, in high-level synthesis, there is a problem with rather common language to such an unusual model of computation you compile. There is a problem to understand what's happening. Some small changes in high-level code may change drastically in synthesized code. And intuitively, you may think that I see this loop, this fragment, it must match some small pattern of schema inside. But you fail. You see the result is the schema is very large. Then you need some back information. So my impression is without solving the problem from information from bottom up to the user, it is very difficult to perform synthesis from high-level code. What do you think about this problem?
Thank you for your question. May I ask, is it correct, is my understanding correct that you are asking about, so to speak, feedback?
Feedback, yeah.
Yeah, at the present, there is no feedback. However, I understand that it is an important issue, and it will be, the method will be changed in the future to address this problem.
I have impression this very, very complex problem. Important also.
Yeah, just this tool is currently being developed, and we adding different functionality. so to speak, incrementing.
Yeah, of course, of course. It is rather natural, but this problem is not simple.
Yeah.
But without solving, a lot of projects of high, translated from high level to low fail because of this. People can't use it. Not only in this area, but in other areas as well, when the model of computation is very different. More questions? Then there is time already to complete this session. Thank you very much. So the session is over. Now, Alexander, we shall present, invite some another invited speaker. Break. Now break. Only after break.
Hello, everyone. Georgi, can you hear me?
I can, and now I hope you can hear me.
How is it going?
Good. I just finished my lecture 15 minutes ago in another building, so I just made it to my office.
Okay,
So how is going on the conference workshop? What was the right name?
So, okay, dear colleagues, let me introduce Georgi Gaydadjiev. He's a professor of University of Groningen. He received his master's degree and PhD from Delft University of Technology, and he's currently a full professor in innovative computer architectures at the University of Groningen and a honorary visiting professor at Imperial College, London. So, welcome.
Thank you, Alexander. So, should I share my screen? So, let's do that. So, do not mind. Come on. Okay, nice. I have a little bit of many presentations open because I have another class in the afternoon. Okay, welcome everybody. Thank you, Alexander, for a nice introduction. So I hope the SYRCoSE is going quite well and you guys are having a lot of fun. So let's talk about something different. And I start with a controversial slide here. The slide basically is something about scales and sizes. And I can see my screen with some delay, which is good. So somebody had nothing better to do and made this estimation how big the volume will be of all the 200 quadrillion COVID-19 viruses of a size of 125 nanometers. And, you know, depending on, did you consider the spikes as part of the volume or you consider them as just ideal spheres, you can squeeze them between 120 and 160 milliliters, which means it will, all of them will fit into the can of Coca-Cola as we know it. Now, this tiny creature, right, structure, whatever we call it, really changed our life. We start meeting each other less often. You know, we're locked down at home, and you know, then you say such a tiny structure with some very interesting properties can have such a significant impact on the entire life on this planet. And all of these particles can fit in a very tiny volume. Now, if we look at transistors, which are the basic components of digital computers, we didn't learn to build digital computers with anything else. I'm still waiting for our colleagues from physics to come with the first really working quantum computer instead of nice stories and promises that in 10 to 15 years, there will be a quantum computer that works. I'm old enough to have hearing that promise for several times now. Transistors are much smaller, right? Currently, 2, and I know that TSMC is working on 5 nanometers, sorry, and TSMC is working on 2 nanometer gate size. So they're much smaller, and there are many more of them. Somebody estimated that in the period between 1960, when the first transistors have been made on silicon, and a couple of years ago, 4 years ago, well, give or take, you know, they were produced 13 sextillion of those devices, obviously part of small, bigger, embedded, you name it, computing systems. Now, what does it mean that we can really have our life being heavily influenced by very tiny structures doing some kind of either biological function or electrical function, carrying tiny currents back and forward, implementing Boolean functions, and out of these building computers, we can change our life on a big scale significantly, because we know computers, they really change the way we live, actually. They infected us, much worse. I would not be able to run my schedule without this device, because if something does not exist in this device, it does not exist in life. And I missed even a PhD defense of a colleague of mine a couple of weeks ago, because they changed and invited me to the committee in the last possible moment. I never got an email or invitation in my agenda, so I was in a completely different city, unfortunately. Anyway, coming back to this technology, it used to be general purpose. So digital computers used to be general purpose, programmable, these universal Turing machines, I'm sure you know about all of them, that can perform any computation given enough memory footprint and enough time. However, with making this transistor smaller and smaller, we start reaching some physical limits. And the first one was the frequency. We could not make them switch faster. So basically, this is when we start getting this multi-core. The processor designers, they are lazy. They say, oh, we have all these transistors. We cannot run them faster. So we cannot make a unified single core processor that runs at a higher frequency. So we basically split the transistors in two and make two processors on the same silicon die. Then they start making 4, and they start making 16. And then NVIDIA comes and start making hundreds of them, right? Much smaller. Then at some point, we could not let them operate at the same time, because even though they are very tiny and the power dissipation is very limited, the integrated effect of all of them switching and dissipating a very tiny fraction of thermal energy, this will overheat the entire silicon plate, reach the melting point, then we have liquid. We do not have a solid state device any longer. We have some liquid thing where the transistors and their gates and drains and source start floating. So in this soup, we cannot do more computation. So that's why we start not switching all of them at the same time, as you can see on this graph that Peter predicted many years ago, 20 years ago. So we start building hybrid systems. And then naturally, when we could not do anything better, we start building special purpose or custom computers, basically that now the silicon in some level is specialized to the task that it is executing. I'm not talking about full custom ASIC functionality. I'm talking about custom computing accelerators in this case. And this is something that we have seen also in other fields of biology, so life-created heterogeneous processing engines, which are like our brains, right? We have these regions, and each region is specialized in certain function. So the cerebellum here is really responsible for our balance, you know, that we can stand up and stay stable on the two legs and really do not fall out even when the strong wind is pushing us, or we are on an unstable surface like the boat surface. We can very nicely balance with our muscles on the legs to stay on two legs. In medicine, every doctor at some point starts specialized simply because doing all these functions in a more efficient way is the only way. And actually, even in industry, and Adam Smith, which is one of the classical scientists in economic theory, he just says that the specialization is needed to indeed boost the productivity of any engineering manufacturing system. So here you should think about these production pipelines that, for instance, manufacture cars or bicycles or bake cakes or bread. You do not have a manual labor there. You have a manufacturing line that is specialized at each stage of the processing doing a certain functionality. So this special purpose operation seems to be a natural way of evolving the computers in the future, as Peter was predicting 20 years ago. But of course, Peter would know because he is also the designer of the cell processor around that time. Now, so what we can do is indeed, we can continue the stupid game that the vendors are doing, making these symmetrical multi-core systems where there are 4, 8, 16, 32, 128 processors on the same silicon die doing exactly the same, being general purpose. Or we can use these transistors to build special purpose accelerators. And this is kind of this heterogeneity at that level. And obviously then we can do all these individual sets of functions much better, much more energy efficient, quite often actually even faster. But in the current situation, we're very interested in the energy efficiency. How much energy I spent to do a certain computation. So definitely the heterogeneous / special purpose accelerated systems make a lot of sense. However, the big question here is how do we program them? Because we know that it's a huge nightmare to program even these multi-cores, right? Having a workload, distributing it evenly across the available cores, spreading the data again evenly, preventing the contentions or load balancing the execution of this parallelized program is a very tough problem. Some of my colleagues would consider that as an art than a science or an engineering ability. And imagine now that we have these accelerators, each of them having their own execution model, their own programming model, their own memory space, their own way of dealing with data and the processing over that data, right? Some examples, you know, all of them, the GPU devices. It used to be a graphical card. Now we're using it to do some high-performance computer applications like linear algebra operations at large scale, because we have these hundreds of tiny processors that can execute the very same sequence of instructions on a different part of the data set. So we can do huge matrices and really spread them very nicely across these execution resources. Fpga cards, maybe you have heard about them, maybe not, but you should think about these chips. So in the GPU, you still have a processor that is fetching instructions, decoding the instructions, executing the instructions, having branches, right? Because sometimes you execute the next instruction, sometimes you want to jump back to the beginning of your loop. Why is my slide progressing? I have no idea. Anyway, coming back, and there are recent accelerators, and as you can see by the big vendors like Facebook, Google, a lot of artificial intelligence workload, right? PyTorch, TensorFlow, powered deep neural networks are used in many tasks. So for this special matrix style operation, because the training is nothing else than backpropagation through some large matrix of coefficients depending on the structure of the neural networks, you know, they build special processors to be very efficient in doing that task. Anyway, this is not new. Some other colleagues like Yale, they were advocating about this specialized hardware for many years. So Yale was unfortunately calling them refrigerators, and he was making the parallel to this player of American football, right? Yale is in the University of Texas in Austin for many years after you know, Berkeley, and then the University of Michigan at Ann Arbor. But he was looking at the trend, right? First, in Intel, we had this coprocessor. You know, we had the Intel processor 286, the 16-bit version, and then we had a 386, which was doing the floating point operations. It was a separate chip, right? We did the dedicated arithmetic, right? We had a piece of hardware, very powerful, that really could do very efficient floating point operations, really needed for scientific simulations, for large scientific engineering problems that solve some differential equations, for example. Then silicon vendors brought these floating point units inside the chip. So instead of being a separate chip, then this became part of the main architecture on the follow-up Intel processors. Then we have start seeing some vector extensions for streaming, audio, streaming video, digital signal processing. Then we start seeing I/O processing accelerators, then some complex operators to do some coarser and coarser grain functions that are really useful and quite often used in our computing systems. And then indeed, recently you can see even extensions, even parts of the system on a chip that is doing entire neural networks, as this accelerator we have seen on the previous slide, or things like compression encryption. So what is the parallel with William pairing? It is that you switch them on only when you need them. So you see, he's a big guy. He cannot run fast. However, in this game of American football, nothing to do with our football in Europe, you know, this is like a rugby, but with all this funny equipment. And they have this more static approaches of crossing a line. So when they're very close to the final line, you just have to get the ball over the line. They will bring this really big guy there. He will hold the ball, and then 10 of the other team will jump on him, but he will be still able to walk across the line. He was really specialized to do exactly that task. If the state of the game was completely different and fast running was, you know, required, this guy was sitting on the spare bench. So he was kicked in only when it's needed. That's what we have to see these accelerators. And then we should be able to indeed program them to do the right job at the right time and be able to switch them on. But there is a problem, right? Because all these different accelerators, they have some different view. And this is just one example. The CPU has some implicitly managed cache memory hierarchy, right? This spatial and temporal locality of accesses to the main memory is used, is benefited from to load certain pieces of addresses from the main memory, which is very costly to access, costs hundreds of clock ticks to read from, but they are cached in a faster memory, much lower capacity, obviously. But this is done statistically. So when the memory is full, some line has to go away. And then, you know, this is the so-called cache overflow, and then some cache misses will be experienced. So some data will not be on the level 1, level 2, or level 3 cache, and it has to be fetched from the main memory anyway. But then a much bigger chunk of data will be copied over with the hope that the data that we needed will be reused later, but also the neighboring addresses will be somehow necessary to the computation. The basic operations is just a scalar operation. We have one element being word or byte or whatever it is for the processor that we consider that is doing some operations like multiplication or addition. The GPUs, they assume more vector kind of operation where we have a lot of processing elements that can do the basic scalar operations, but in parallel. So we do not have to write a loop to do them sequential. We just can, in sense, unroll the loop into these thousands of tiny processors on the surface of the GPU. And then the operations are also at that level. So basically you do vector operations instead of scalar operations. And the third example we have seen a few slides ago, the tensor processing kind of units, they work on tensors, and the operations that they perform are tensor operations. And obviously, you see that the green part in the middle is kind of a mixed. There are some levels of cache that are statistically driven, but there is some shared memory that the programmer has to explicitly program, move data from the device memory to the shared memory and vice versa. The TPUs is even worse. The activation buffer and the accumulated register file and the weight FIFOs, they're completely different data structures that are really specific for these tensor operations that we are doing. So can we build code that we ideally should be automatically compiling to all of these platforms? And let me tell you, there are many more than those. These are just 3 examples. Some people say yes. So the cycle, and you can look at this link, they claim that they are able to compile the same source code for FPGA accelerators, for NVIDIA CUDA devices, for AMD ROC GPUs, but also for Intel multi-core processors and Intel accelerators. Let me tell you, that's going to be very tough. And I'm giving you just one example, that if you even look at one specific vendor across different device generations, but also versions inside the same device generation, you will get surprises. For instance, the Kepler GKE 110, and this was part, by the way, of the lecture that I just finished, supports dynamic thread spawning from the device side, right? On all the older devices, including the Kepler GKE 104, which is the same family of devices. You could load spawn grids of threads only from the host code, only from the CPU side of the system. So the GPU kernels, they could not spawn grids of kernels on the device. The GKE 110 does it. So writing a code that will run on both, quite difficult, efficiently, right? Then this is how, for instance, the LU decomposition will look like. I have to do a lot of transactions between my hosts. So this is basically all the blue lines are executed on the host CPU, and all the yellow lines are commands sent to the GPU device to do the different phases of the LU decomposition iteratively. And then, of course, copy back the intermediate results. And ideally, at the end of the outer loop, you will have this triangularized version of the input matrix after, obviously, the elimination process was finished. On devices like these more recent Kepler devices and later, right, all these current NVIDIA devices, you can write the code much simpler. You can spawn the kernels when you need it, the grids of kernels, right on the thread from the device side, and have this dependency tree dynamically generated, doing all the work, depending indeed on the context of the elements in the matrix. And at the end, you just have to do the synchronization, right? I have to just make sure that now my host is aware that the CUDA device finished executing, doing the LU decomposition, and I have to copy the result over. So obviously, in terms of execution graph, there will be some differences. There's something flying here behind me, I see on the screen, very nice. So you had to do a lot of synchronization and copy in and out between the host CPU and the device, right? All of this going to the PCI Express interface, much less efficient. And of course, you could do that only in lockstep, while I can spawn really fully asynchronous dynamic trees when some of them will finish earlier than others. But at the end, I will get my LU decomposed input matrix. So basically, looks not so trivial as our colleagues promise, that you just write a single code and they by magic compile it for GPUs, CPUs, FPGAs, probably for tensor devices. I don't believe it. So looking from the more general point of view of parallel computing goals, right? Basically, decomposition of the problem in whatever way and the data is efficient, because we would like, it's a key, sorry, we would like to basically divide the big piece of work that we are doing in a number of small, simpler tasks, working in parallel, being dedicated to this hardware heterogeneous resources that we have, and solve the overall task. And you know, in parallel computing, you cannot guarantee the order. So all these functions that we decompose and execute in parallel, they should have these properties of associativity, right? Independent on the order of how we execute the separate tasks, the result should be the same. Commutative is another nice to have property. But anyway, so the programmer structures the code and the data, and this is very essential. That if you only do the code and forget about the data, your performance is going to be really bad. Because what we want to reach is one of these three goals. We have some existing application working on some existing data, and we want to make it run faster on a bigger system, right? We have to do some transformations to exploit these additional execution resources, the additional memory capacities, the additional communication bandwidths, because even if you have a very capable silicon that can do super duper zillions of floating point operations, but you cannot feed it with data, your performance will be as slow as the data rate to move the data in and out of that specific accelerator or that specific part of your system. Anyway, or we want to, while getting the bigger parallel computer, we want to solve bigger problems, right? We want to make, for instance, also a more precise model. So all of this are goals of parallel computing effort. And then some recipe, but let me tell you, this is a high-level indication. Find the concurrency of the problem. Structure the algorithm so that this concurrency can be efficiently exploited, ideally, while considering the system that you plan to program. And then implement this algorithm, just picking some suitable programming environment. You can use OpenMP, you can use MPI, you can use CUDA, as we mentioned earlier, or you can use TensorFlow, right? If you're doing tensor operations and you do some deep neural network simulation and training, yeah, you know, why not? And then, of course, you execute and fine-tune the performance of the code. So think about it. Step number 1 and number 2 does not require even writing a single line of code. It really is thinking. It's analytically understanding. It may require some profiling to understand what's going on with the code, to understand the data set better, to also understand if this is the best algorithmic approach, because you may be given some initial code that somebody, typically physicist, wrote without any, you know, deep understanding of how parallelization works. So modeling thinking is really very advisable for programming parallel computers, because if you start coding and then debugging and then improve it, you will be rewriting a lot of your code and you'll get surprises, because in addition to the parallel structure that you have to kind of load balance on your system to use the resources efficiently, you will have other nasty effects like deadlocks, race conditions, you name it. It is much more complex than sequential programming. And if you start with the wrong system architecture, definitely a lot of code has to be rewritten. Then, finding and exploiting is a big challenge, and really it requires this parallel computational thinking, and also thinking about the both parts of the computation. Doing the parallel computation, right? How I can parallelize it, but also not forgetting that the data has to be moved in and moved out across the different execution units and the different memory levels or nodes in your system. If you do not model that, you will get basically into the mistake of the PRAM. So there is this random access machine, the abstract model for the von Neumann sequential machines, that is really very powerful. We can write a C code and estimate how well it will perform. There is another similar model that ignores the latency of memory accesses across the network system, And then this model hints you toward parallel algorithms that really very poor and very poorly work on a real machine, simply because you cannot move data for 0 time. We have the speed of light, right? If there is a 1 meter cable between the two systems and I have to move some piece of data, you know, the latency, I cannot beat the speed of light. It's going to be there. It depends on the physical distance between the two systems. And even on a tiny centimeter distances, this is not negligible. It is in the order of the clock frequency of the current modern processors. Anyway, dependencies, task execution, but also side effects of numerical accuracy. I don't want to disappoint you, but floating point implementation, right? It's a digital approximation. There is some discretization. And depending on how you add 3 numbers or subtract 3 numbers, whatever you like, if there are some big values and small values, depending on the order, do I do A, B, and then C, or I do A, C, and then B, my result, if I'm unlucky, may diverge even by 20%. Because of the discretization. Anyway, and of course, the dynamic range of floating point numbers is obviously much worse than fixed point Boolean, binary numbers. And then, of course, all these other overheads of synchronization, overheads of moving the data in and out, overheads of initializing something like spawning tasks, spawning CUDA kernels. You know, load imbalancing will cause inefficiency because the slower thread will let all of the faster ones to wait until the synchronization barrier. Saturation of critical resources, like, you know, flowing over the caches in your system, right? Certainly, you scale and then you get a degradation in performance, and then you start pulling your hairs out. You say, what happened with my system? You know, all of this is something that you have to understand if you want to be a good parallel heterogeneous computer programmer. So the concurrency can be done in decomposition, that can be done in 2, but there are more than these 2 basic ways. I can, like in a manufacturing pipeline, specialize the different stages of processing and have this pipeline to task 1, task 2, task 3, task 4. And if I have a lot of data to fit through this sequential pipeline, I can process them in terms of time simultaneously. It is indeed similar to this car manufacturing process that I mentioned earlier. But you can do data decomposition. The CUDA devices do that, right? I have this large matrix of thousands, if not millions of elements, and then I work on tiles. I work on a column, and I work on a row, and then I do this computation and gradually accumulate the final result. Then you can try to reorder the tasks. You can try to group the tasks or condense work in one task as respect to the other in order to balance the latency of the execution of the different tasks. And of course, data sharing causes a problem as well. So in an ideal world, as Matson and a few of the other colleagues said, the compiler should be able to parallelize, but auto-parallelizing compilers that can work nice even for a trivial computation like matrix Veltro multiplication are still underperforming. Then selecting the algorithm, again, you can organize by task, like is the case with the CUDA devices, but then you can have a linear pattern, you can have recursive pattern, and then of course, in the one case, you just exploit the task parallelism up to the limit of your system, how many tasks I can facilitate, like in a CUDA device. A recursive, I can dynamically solve my problem by solving smaller and smaller pieces, like sorting using tree structures. But you can also organized by the data, put the data central, and then do decomposition, right? Climate simulation is, I have a geographical area. I want to simulate there the air pressure, temperature, airflow, humidity, you name it. And then I can divide it in squares of 10 by 10 kilometers. And if my computer is powerful, I can reduce the grid size and have 1 by 1 kilometer. So I do the same computation, but I compute many more of these unit blocks of the entire geographical region that I want to simulate the weather for tomorrow, for instance. And again, you can have algorithms like fractals that are data dependent, so they definitely should be computed in a recursive way. And there is another way, and as I said, this is just some ideas how you can think about the parallelization. This is the data flow way. Then you assume that all your data is like this, let's say, parts that enter the manufacturing pipeline that builds cars or bicycles or coffee machines or whatever they build, and then they are gradually assembled. So there is a flow of data rolling through the different stages and continuously being pipeline. But you can also make it data-driven. Basically, you can make it, okay, I'm going to compute something only when the data arrives. Is this more efficient? Yeah, for some algorithm, this will be more efficient. Programming models, execution models, they're also different. The CUDA uses the single program multiple data, which is an extension of the single instruction multiple data that you may have heard of. The only difference here is that all these threads that simultaneously, all these processing elements that simultaneously execute the same sequence of instructions do not run in lockstep. So the thread has some binary instruction set, but some of the threads may go farther and some of the threads may be delayed. Single instruction multiple data runs the very same instruction across the different vector lengths. Now, that's the only thing. But you can have master worker. I can have this queue-based system when I can just queue jobs, and then there are some pool of workers that will dequeue jobs and do the job and basically do the work. You can have a loop, explicit loop parallelism, like OpenMP does. And you can have fork and join. This is the common model of the pthreads that allow you to dynamically create execution trees of parent-childs that can communicate and do this simulation on demand when something is needed. Like I'm simulating some computational fluid dynamics, like the hot air flowing out of my jet engine, and I have to really know how the temperature will develop and how the gases will spread after that to make sure that, for instance, I keep the motor far away from the tail of my airplane. Otherwise, I'm going to burn my tail and then the airplane will crash. This is not nice. Anyway, now the data models can be shared data, like the OpenMP. It can be queued, but it could be also some distributed array, like the MPI style of communication. So a mix of all of this exists. So picking the right set is difficult. And this is just an indication. Again, Matson did his best to summarize that and say the different execution models, they kind of suit better or not at all the different execution models. Like I cannot use the loop parallel and build a pipeline, because the loop parallel is do this body on that many parallel threads. I cannot pipeline it. They are in nature implicitly parallel. And this is a good thing to start. But of course, I can just give you some very simple example. And this simple example is trying to do something of 1 million steps. And then the computation is the same, right? This dot, dot, dot here in the body is something that I want to do in parallel. And then my system supports certain number of threads. So an obvious thing is to do to see how much work I can do at once, which means I take this ratio of the entire number of steps divided by the number of threads that my system supports, and then depending on the thread ID, I do certain segment, right? Thread 0 will start with address 0 and go up to the first segment. Then the thread 1 will start with the first segment and go up. So I basically chunk a lot of equal pieces from the task and just do them with the available system. Unfortunately, the last iteration is undeterministic because the vector length is not power of 2. It's not power of the number of threads that I have. So there will be some reminder, which will be a problem because the last iteration is gonna obviously, or the last set of tasks in my system will take longer or shorter, but there will be unbalance between the execution latency. So not nice. I have to really do that. And in the CUDA devices, it's even another nightmare called branch divergence. And this is something that we can talk about on another occasion. But on a very tiny level, the CUDA devices, they execute a bunch of 32 instructions in a single instruction multiple data way. So they really do the same instruction along 32 different data elements at the same time. And if indeed in your code there is an if statement, some of the 32 has to go left, some of the 32 has to go right. How I do it? I cannot do it. And this is a big problem. So how you can do it? You can evenly spread the load. You say, okay, I just compute that using integer division and get the reminder and then spread the reminder equivalently through my threads and create this load imbalance. But this means that there is another if else statement that really now checks about the reminder and then adds these additional elements. And this is a problem, to be honest, because this will create this thread divergence that we said. So in this case, what we can do is we can just interleave on a very fine grain. We said the first thread is just working on the very first element, and the element after all of the other threads got the next elements in the linear order. And then this, linear access repeats, and this is the best load balance in this case, because, you cannot be wrong more than one on the last piece of thread blocks. And then, of course, the branch divergence is also only into the last block, because all of the other threads into the previous sections will just do exactly the same instructions, exactly at the same time. So this is how this looks gradually. The first version will have a bunch of equal length segments, but then the last thread has to do more work. And it can be as bad as thread -1 elements, because this is this discretization happening at the end, right? Then the version 2 evenly spreads across that, but we have more branch divergence inside these execution blocks. The version 3, very nice for things like sorting, for workloads like convolution. This is a very good approach. When you have all the threads fetch one element of the first segment, then all of them move to the second segment. So basically, this translates in a coalesced memory actions to the memory system, which is the best way of treating the memory. Memory really can efficiently read data in a linear order up to a certain capacity that is called the burst size of that given memory system. So this last interleaved access is very interesting for some workloads. For other workloads, it's going to be terrible. And this is the point, that you have many options, but how you choose the right one for your algorithm, for your data, up to you, because also on a different system, this will require probably a different approach. And this is why modeling the system, understanding the algorithm, understanding the data and the requirements is essential. You cannot do only one of the three pieces, unfortunately. And this is another example before I finish, to be honest. There are two OpenMP now codes, and then I tell you, okay, this one is going to work much faster. And then the question is why. They do exactly the same pi function approximation across n parallel sections, right? This is the whole OpenMP parallel 4 that is done. And then n iterations are done, sorry. But the question here is that we should mind the private action here. See, here the accumulation is done obviously in safe order because this is the pragma critical, which means there is this write, execute, write atomic action guaranteed. But many of these threads will try to update the area at the same time. Here, all of the threads accumulate their own local sum for the entire number of iterations. And only at the end, this reduction is called, that the final result of the iteration is going to be congesting on the incrementation of the, the global area of the final result. And then the pi is obviously the division between the area and the number of iterations that we did. So, but there is more deadlocks. I'm not going to even talk about deadlocks, but you are aware what this means. And in the traffic jam, we had them in parallel computing. How to formally avoid them? Oh, this is an unsolved problem. So there is a good news. A lot of open questions and really exciting challenges ahead. And with heterogeneous system, this is becoming even worse. So, meaning even better. A lot of interesting work can be done. Need for semi-automated design tools. Fully automated design tools, forget it. For very specialistic tasks, you can build tool. It can help the human designer. But this insight of understanding these 3 dimensions, the system architecture, the problem that has to be solved using 1 or 2 or 3rd algorithmic approach, and the data and its requirements is needed. And no formal approach exists, I'm sorry. Then scalable libraries and runtime systems, really needed. Design methodologies, auto-tuning tools, right? Because the system typically runs multiple workloads. Depending on the status of the system, you may have to tweak some knobs to make your algorithm or your workload run better. Migrating between these different subsystems from one system to the other, tough problem, unsolved problem, but also profilers for parallel execution, debuggers for parallel execution, where I put my breakpoint. I have this execution tree, which is dynamic, where I put my breakpoint, how I see the state of my system. Typically, the state is huge. Interrupts do not exist in this type of accelerators. Formal verification. Can I prove that the code that I wrote does not contain deadlocks? If you can build such a tool, you will become very rich. Bill Gates will be asking you to give him some money, and many, many more. So basically, to master heterogeneous system, you have to really build the computer for the task that you have to. And typically, it is some challenging problem that only very powerful computers can solve. So avoid wastage, improve utilization of resources. And resources are not only execution resources, memory is a resource, interconnect bandwidth is a critical resource. Very often, systems are bounded by memory bandwidth or communication link bandwidth. Then compute only what the problem requires, right? If, for instance, I need to compute the weather for tomorrow and I can do it in 2 hours, it's just good enough. I should not accelerate it to be done in 2 minutes. Doesn't give me anything. I need it tomorrow. I do not need it in the next minute. Then working together with domain experts while programming heterogeneous parallel computer is very essential because they know what the problem is. They know what the computer should be giving them. And sometimes something that is not giving the best precision is good enough for them to do the job, like predicting where the oil under the surface of the earth is or where the gas is, So starting from the algorithmic approaches, understanding what needs to be done, building the system is the right way to do that. So that is my talk. Are there any questions? So
I would like to start with a proverb that you mentioned in Russian in your last slide.
Ah, very good. Yes.
And then return back to slide with pi approximation.
Which are the pi approximation? Yes.
Pi approximation.
Exactly.
Basically, well, you explained very well why the right-hand side is faster than the left-hand side. But since these both programs are dealing with floating point, basically it is not clear how to prove that they are equivalent. And maybe in the right-hand side program, accuracy is not so good.
I agree with you. And
so
the floating point is
observation and your comment. Basically, formally speaking, since we don't know what is floating point exactly, we even cannot prove that they are equivalent.
No, but the whole thing is that's why I mentioned that if you can have a formal proof of correctness or formal proof of, even that there will be a solution, because, right, solvers, they may or may not give you a solution, right? Solving that problem analytically, solving that problem using some mathematical apparatus, as Gödel says, it is not quite possible. So indeed, but the floating point is a really huge problem, because you can run the same OpenMP code on two different processors, even by Intel or by AMD, and the floating point designers may have decided to save on some of the hidden bits that are used to normalize the results, especially when you do addition. And then the rounding will be completely different and you may get surprised. And this is why I'm really telling my students, typically colleagues, that they should do some experimentation with the floating point facility of the system that they plan to program, and rely on the precision, understand the side effects, and then start from there, unfortunately. So kind of empirical discovery of what the designers economized.
Okay, thank you. More questions? I have a philosophical one.
Good.
So yeah. So you said there are two approaches to computing, not only to computing, unification and specializations, general purpose computations and application specific computations. So, and you said that the main trend now is specialization, domain specific computers. So what the future of general purpose computers? Does it exist?
They will be always there. See, you need a control processor that is doing the heavily control flow driven execution flow, like running the operating system, waiting for the user to press a key. You don't want to do that on a specialized accelerator. You can program it, on GPU maybe, but it's going to be waste of resources. Really, the general purpose parts, right, they will be more and more used as this master of these heterogeneous resources, like this orchestra, like the dirigent of the orchestra that says, okay, in this certain situation, I need this refrigerator switched on because the context of what I'm doing right now requires me to do that. And then they do the dull, dirty work. And when they are not needed, a next set of special purpose accelerator will be switched on, which basically also is in line in what happened some decades ago This is known also as the dark silicon, when designers were unable to power on and use actively all of the transistors that they can manufacture on the same silicon die. So, and then, you have these special purpose accelerators, they're switched idle, actually powered off, and when you need them, you switch them on. However, the logic, when you need them, still has to run on a general purpose processor.
Okay, thank you. More questions? So no more questions. Thank you, Georgi. So I know you're pressed in time.
Yeah.
So thank you very much.
Gonna be leaving. I wish you guys a productive event, and I hope to see you at some point.
Okay.
Take care. Bye-bye.
Now it's time for lunch.
on this website of Open Web Application Security Project, you can find a list of the most popular attacks on web services, as well as attack patterns. In this work, authors show that the web service vulnerability detection can be performed by solving automata equation over the concatenation operation, and this approach allows to determine the set of input actions on the web service that can lead to an attack. In the slide, you can see two types of such equations. Consider first equation. Automaton S describes the set of insecure requests to web service. Automaton A is a prefix of this request, and it is a fixed part of this request. And unknown automaton X matches the part of the request that the user enters. It should be noted that the ways of solving such equations are very well studied. In some cases, it is necessary to take into account the time aspects when checking the vulnerability of web services. And to do this, we want to use the timed automaton model, and we need to check the possibility of solving equations for timed automata. Consider the model of finite automaton. It is a 5-tuple as it's a finite non-empty set of states with the initial state as 0. F is a set of final states. J is an alphabet of actions, and lambda is transition relations. In fact, timed automaton or automaton with timeouts is the same finite automaton, but with the addition the timeout function. In this example, we can see that in the state S2, there is timeout transition. Timeout transition. This automaton in state S2 wait the input action J2 during 3 takt of time, and if action J2 is not applied in this time, this automaton goes to the state S0. The timed automaton has an internal variable of clock. This variable indicates the times since the start of the times automaton. Timed action is a pair JT. J is action, and this timed symbol indicates that the action J is executed at the time instance when the value of the timed variable is t. A language or behavior of timed automaton is a set of all accepted time sequences in initial state. This timed sequences consist of timed actions, a chain of timed actions. In this example, you can see accepted timed sequences for this timed automaton. And it should be noted that this timed action correspond to transition to timeout transition in where 7 is a value of time variable. The concatenation of timed automaton A with timed automaton B is the timed automaton A point B, such as the language accepted by this concatenation contains each timed sequences alpha beta, such as alpha from language of A and beta from language of B. The solution of an equation, there is timed automaton x prime, for which the concatenation R x prime or x prime point B is equivalent to S. And a timed automaton largest is called the largest solution to an equation if it contains every solution of the equation. In our work, we consider two ways for solving timed automata, two types, and we consider two ways for solving such equations by using submachines and by use automata abstractions. Consider the first way for first type. In the first step for the timed automaton S with the initial state 0, we check whether this submachine A prime with the same initial state that is equivalent to A. If such submachine A prime exists, that it is necessary to derive a union of all submachines of the timed automaton S with the additional state A, where A is small a, is the final state of the submachine A prime. If the union is not empty, when we get the timed automaton largest. And the final step, we construct the concatenation of the timed automata A and largest. If the concatenation equivalent to S and largest is largest, and then largest is the largest solution to the equation. Otherwise, equation is unsolvable. And it's a similar way we can find the solution for the equation of second type.
Consider the second approach to solving equation over timed automata. This approach based on automata abstractions. Consider simple example for first type. We know the automata A and S, and it is necessary to construct corresponding abstractions for it. We transformed the transition, the timeout transition into chain over I actions. I action, it is one union of time. This approach was considered in various works of various authors for finite state machines. After then we have this equation, and in fact this abstractions is classical finite automata, and ways of solving this equation is very studied, and we can find solution of this equation. And then we can transform we derive corresponding timed automaton X prime. Thus, we considered the problem of solving automata equations over the concatenation operator, and we we propose to approach for this. And it should be noted that these approaches need further research and development. It should be interesting to access the complexity of such approaches, as well as to apply them to verify security of real web services. Okay. Thank you.
Thank you very much. We are ahead of time. Now we have at least 5 minutes. Your turn, please. Yeah. Right.
Thank you. My question about scalability of this approach. So there's some relations between size of web size and size of complexity of consideration and equations solved. So when you will verify or analyze a real website, it depends on the complexity of this site.
We try to verify vulnerabilities of real services for equations over classical finite automata. And was a service of shadow Tomsk State University, and we find the vulnerability to XSS attack. And now
but
we can,
I'm interested in some estimates of size of is it important? Maybe 10 nodes, maybe 1,000.
1,000.
1,000. Okay. And in this case, do you need some tools for proving analysis?
No.
Other questions, please?
I am absolute dilettante in this area. I only from time to time listen to the students led, supervised by Yevtushenko. But so my question is very general. Are the theory give some new result compared to classical automata? From a dilettante point of view, there is time can be by certain intermediate states which change. If I have timeout of 5, for example, I can insert 5 intermediate change. So first impression without deep understanding that the same problem can be reformulated in classical automata. No, maybe just coefficients, maybe some just complexity will not asymptotic, but just up to coefficient. Or my opinion is wrong. Of course, you can't give me a lecture about this, but is there some proper results of time automata which have no comparable results in classical? Or
the model of automaton with timeout is not same the model of classical time. For solving problems with automata with timeout, we need the no.
I also have a short question. Question is short, but I believe answer will be long. So let me reserve my time during dinner today for asking you the question. I would not like to overuse my right to ask the question. So let's send speaker, but indeed I would like to reserve time to ask you a question during dinner today. Thank you. Let's send speaker.
Thank you very much.
So we are exactly on time. The next speaker is Roman Kholin. He will present joint work with Denis Gamayunov, both from Moscow State University, Lomonosov Moscow State University, detection of remote code execution vulnerabilities, sorry, using abstract interpretation. Again, I will stand up before 5 minutes ahead of your time slot.
Okay, thank you. Hello to everyone. My name is Roman Kholin, and thank you for your invitation me on this colloquium. And today I'd like to introduce my report on this topic, detection of remote code execution vulnerabilities using abstract interpretation. Remote code execution, known as RCE, this is attack among the most dangerous attack nowadays, and they can it can lead to disclosure of security data, confidential data, unauthorized deletion of data, device control interception, and some other vulnerabilities. And so I like to propose a method and tool for automatical detection of these vulnerabilities, and our approach based on console execution. So let's start. Let's look on this simple example. It will help us to define some definition. This is code. This is web server, and code of this server is written was written on JavaScript, and it's vulnerable because we as a client can send by URI by name some data through query parameter called name, and if the client of this application send some data which make this SQL query the where statements became a tautology, the client will get all information from this table, and it's bad. It's not a typical behavior of this server. So what kind of data we should send? We should send well-known attack vector 1 or 1 equal 1, and so this type of function like db.each we will call sensitive function. What is the function like functions like that? It's a function which executes some code, and this code could be corrupted by user input, like in this example. So, and another example of sensitive function or hotspots is a val function, and this query we will call the query to the sensitive function. So the goal of my study is to create a tool which will help to security auditors and penetration tester to automate the finding of this type of bugs, and so we try to solve task of white box analysis. This means that we have all source code of the application, and we want to get a small number of false positive mistakes, because all these mistakes pen testers should check, and we don't want that he or she will do extra job. So now I will describe tools and techniques which I used. First of all, it's a Jalangi tool. It's a framework for writing dynamic analysis. this tool instruments the code and allow us to implement some callbacks. What's it mean? For example, after Jalangi instrument this code, we will take code like this, and all red words on the slide is callbacks, and these callbacks we can implement for some useful analysis. For example, we can collect the trace of execution program and use it somehow. The next one is Z3. I think the auditory knows this solver as well. It's a satisfiability modular series solver, and it allows checks whether mathematical formula is satisfiable or not, or maybe unknown. Maybe solver give up and answer to us that it couldn't check this formula. Consolic execution is a hybrid software verification techniques that performs concrete and symbolic execution, and it allows us to coverage the execution passes of the program, and if the number of passes is finite, this technique will allow us to coverage all program, all passes. So, and one of the tools that implement this technique is exposing test input generation for JavaScript program, and this use Z3 as solver. And the last tool is SQL map. It's a tool for penetration testing. It gets of target application and maybe some information, and give us a vector of attack, or maybe nothing. So our approach is next. We search a call of create server function. It's a function from standard Node.js standard library called HTTP. So this function takes as input another function, some function f from request and response, and instead of execution create server, we will run the function f, and we send as arguments request codes and response codes. What kind of object is it? Request codes contains console variables URL and methods, and response it's almost contain nothing, and then we start execution of our program and search the sensitive function or hotspots. it's the same. And if we find the sensitive function, we can restore the URL and send it to SQL map to verify if it's vulnerability or not. So we check it on our synthetic web application. First application was first application used standard library plus driver of MySQL, and this application contains SQL and code injections, and second application was written on Express and SQLite, and we create this tent to prove ourselves that our tool can examine the large programs. And there are a lot of works to do. First of all, we didn't test it on real open source on a real web application, and we want to do it, but now it's difficult. We don't use information about queries that come to a sensitive function, but we know a lot of information because of symbolic execution. We know universe of input data that could be sent on this function. And we would like to extend our approach on other types of vulnerabilities like XSNs, for example, and model of request prime and response prime is poor now, and we would like to improve this model. Thank you for your attention. Please ask your question.
We have 8 minutes for questions. You first.
Thank you for your talk. I developed some web applications 10 years ago, and even at that time, I used the framework that automatically work around this issue for me, so I shouldn't pay any attention to any SQL injection. And so I'm wondering, does anybody now use direct SQL statements in their code? Or, because from my point of view, almost everybody should use some frameworks that should hide these issues automatically, implicitly for them. And this is also the case for some other attacks as well.
I absolutely agree with you, but you know, the most popular vulnerabilities in the world is SQL injection. So, and in nowadays, it's still actual vulnerabilities.
Other questions, please? Any other questions?
I am not satisfied with my answer. I did develop a web server, so I am, as a previous, I am a dilettante. But I heard that this problem is a very old problem. It was discussed. So more than, and you see some symbolic analysis of classes of strings, propagation of problem. So my question is, actually, either there is a problem of existence of good tools, or maybe there is some theoretical questions. What now the edge point of this research? what was your motivation?
And maybe some addition on the same topic. What is specific technique of concolic testing in your case?
It's not a specific. It's not a specific technique on this tool because all symbolic execution implemented in Exposé tool, so I only use it. And answer to your question, I think the first one, so this problem of existence of a good tool, not and computation power maybe.
Other questions, please? Any other question? Okay.
Thank you for your talk. You mentioned in the title term abstract interpretation. In what sense abstract interpretation is present in your work? Is it inside consolic testing or some other part?
No, only consolic testing.
Only so it's part of consolic testing.
Yes.
Mm-hmm. And in consolic testing, how do you concolic testing? So how do you set the task for concolic testing in the presence of hotspots? How do you set? Do you somehow direct this consolic testing to the point of interest, in your case, to the point of SQL statements, or it's just works out of the box and you just monitor?
The hotspots searched while the program executed. If you know what consolic execution is mean, it's the target program executed several times on the different execution passes, and on every these execution passes, we try to find the hotspots.
Don't try to give some hint to consolic testing. What do you need? Because consolic testing usually tries to cover all parts of the program, not in particular.
Yes, we don't advise to our tool find the particular places in code.
Any other question? If no questions, I have a question. You started your talk with motivation to reduce number of false positive warnings. But you didn't mention in your conclusion. Why do you think that you actually reduce this number?
We reduce this number because we believe that SQLmap is a good tool and didn't and it reduce only a true vector attacks.
So roughly speaking, you did not compare your approach with others similar, and so you cannot provide some statistics or benchmarks.
Yes, it's a problem of my work.
Okay. So nevertheless, you still have this goal. I know. Don't rush, please. I am a moderator. Thank you very much indeed.
Thank you.
Once again, speaker. So the next talk is by Kirill Kobyshev, right?
Right. Yes.
Again, it is joint. Talk with Sergey Molodikov. Thank you very much. Today is very hard sometimes to read English spelling for Russian names. algorithms of test generation from functional specification using OpenIE model and clustering. Speaker is from St. Petersburg Polytechnical University. Please go ahead.
Hello, my name is Kirill Kobyshev. Sergey Molodikov is my scientific advisor. Today we listened a speech about the code generation. It was the first very interesting speech. My speech is somehow related to the speech because it is about the code generation too, but it is more specialized on testing automation. You see the name of the research on the slide, an algorithm of test generation from functional specification written on natural language based on using of OpenIE model and clustering. Let's talk about the relevance of the research. So the topic of the research is located between two subject fields. The first is testing automation. The second is natural language processing. The testing automation is used in long life software development projects where life cycle is continued during multiple years after production release. And I can say that there is an active development during the last 20 years of new tools, new approaches that are listed. Examples of that are listed on the slide. Natural language processing is actual subject field 2. It resolves computer science problems using the rules from computational linguistics and using machine learning models. It is widely used in everyday life. It's used in chatbots, voice bots, on automated first line of tech support, in machine translation of natural languages, in information search engines. So I can conclude that the topic of my research is located in cutting edge and actual subject field. The start point of the research were disadvantages of existing solutions. So the main approach of testing automation are listed on the slide. I found the 4 main approaches. The first approach is classic, when QA analysts should prepare documentation on natural language. Then QA developers should read this documentation and should implement automatic tests and test framework. So automatic tests should use the testing framework. And the structuredness of tests is an area of responsibility of QA developer. And we cannot guarantee that these tests will structure it. So the second approach, behavior-driven development, allows us to guarantee structuredness of tests because the structure of tests should be defined by analyst. And this approach allows us to achieve the common understanding of the system behavior between analyst and QA developer. But this approach is not fully automated. Tests should be prepared manually. The third approach is a set of formal verification methods. These methods allows us to achieve a high reliability, but these methods are not applicable everywhere because of the well-known problem of combination exposure in complex programs. So this method requires the simplification of complex programs and not applicable everywhere. And the last approach is more exotic. I found it in the one paper after proposed to train the neural network on behavior of the source program and to use this neural network for regression testing. But we need, after each new implemented feature, to retrain this neural network, and this approach is not so reliable. So the proposed solution allows to decrease the degree of these 4 shortcomings. The first is a low test structureness. The second is misunderstanding between analysts and QA developers. The third is a low performance of testing system in complex programs. And the last is low reliability. The main idea is the following. The main idea of the proposed solution. Analysts should prepare test scenarios on natural language. This scenario should be converted by our algorithm to automatic tests and to the interfaces of the test framework that is used in our automatic tests. And these interfaces should be implemented by QA developers. Consider the proposed algorithm in detail. So we have 4 steps of algorithm. The first is a preparation of natural language test scenarios. Each test scenario should be processed by our algorithm independently, and each paragraph of each test scenario should be processed independently too. So we passed the test paragraph to our algorithm. It should be transformed to the syntax tree using relation extraction algorithm and dependency tree parsing algorithm. In the third step, our algorithm should convert the given syntax tree to the tree with categorized nodes, and node types should be stored in database and associated with the given tree nodes. And the last step is transformation of the tree with categorized nodes to the Kotlin language automatic tests by one-to-one rules. So I will describe these steps in more details. Let's consider the second step in details. So analysts prepared a natural language test scenario. This natural language test scenario contains a sentence, contains a paragraph. User paid enterprise tariff with price 500. So we used open information extraction algorithm to extract the relationship subject and object. In the current example, the word paid is a relationship. A connected node user is a subject. And we have a complex object containing multiple words. An object is presented in a form of a tree, of a dependency tree, where nodes are marked as parameters and leaves marked as values. So we have parameters tariff, we have parameter price, and we have 2 values. The first is enterprise, and the second value is 500, because these nodes are leaves of the tree. In the second step, we define the categories of each node. We used the global vectors model to define coordinates of each node in semantic space. And we defined the groups of nearest words, of nearest subjects, of nearest relationships, of nearest parameters. And so we defined the type for each node. And in the last step, we transform the given categorized tree to the Kotlin language automatic tests by the following rules that are listed in the table. So the subject should be converted to lambda expression with context, a very useful construction in Kotlin language. It also very useful in automatic tests. If we have two paragraphs with the same subject, then the subjects of these two paragraphs should be united to the one lambda expression. What about the third rule, relationship rule? So we should convert relationship to the function call. So the word paid was transformed to the call of the function paid. The next rule is an object rule. Each object should be transformed to the hierarchy of constructor calls, where each parameter is associated with constructor call. So the root parameter is tariff, and we passed it as parameter to the of the function paint. And we have a constructor call price. And the last rule is a value rule. So each value should be converted to the string. For now, it is only string. Maybe in the future we will transform to the numbers too, for example, depending on the word, on the type of word. And in the last row, we see how the test scenario will be converted to the Kotlin language automatic tests. So we implemented a base of the proposed algorithm. It shows good results on simple examples, but for now, it's not working correctly always on complex examples where subjects or relationships contains multiple words. In our solution, we used Java, we used a Stanford NLP library for text preprocessing, dependency tree building, and we used this library to use the model OpenE. We used MongoDB to store nodes categories. So we want in the future to calibrate the proposed algorithm. We want to finish development of clustering of multiple word nodes of the tree. And we want to consider alternative models, alternative to OpenE and alternative to global vectors models, because maybe another models will show the better results. That's all. Thank you.
We have 5 minutes for questions. Any question, please?
Thank you for the talk. Maybe you already encountered such the situation when, for instance, analytics testers use other words than programmers. For instance, tariff may be denoted as completely by other words in the program. And have you any ideas how to find the appropriate entities and appropriate names?
So we particularly solved this problem by using of clusterization of the similar words. So we used the global vector models to define the words with similar meaning. So it is a part of our algorithm. The main goal of the third step of algorithm to avoid this problem.
Excuse me, I didn't understand your term structuredness. Could you provide some example? Good structuredness at
yes.
pure.
We have a well-known anti-pattern where automatic tests are not structured and doesn't reuse the same steps, the same test steps, and contains a lot of code duplication, for example. What does which test? Sorry. The unit. Yes. In the unit, I don't sure that we can use this tool for unit test. I think that it's more specialized on integration tests, end-to-end tests, maybe UI tests. Yes, because it's not applicable for unit tests. Yes.
Any other questions? Okay.
How do you think will your work would be correlated with test-driven development? Because as I see here, we just simplify the process of software development. For example, if we have some new feature for an enterprise, for example, product, we just communicate with our customer. So we form a specification in some documentation, for example, portal or some different instrument. And your solution could simplify our development by giving us ready to use tests that could be run automatically. So are you looking further for integration between these tools for writing specification and your approach?
Yes, I guess it could be used, but the description from customer, there is possibility when the description of expected system behavior that was written by customer is not accurate. But if customer will take in account some conditions related to our solution, then I think that our algorithm, our method will be helpful in such case.
Okay, let's thank speaker. Oh, very short question, very short question. We still have 1 minute.
Okay. Short question. Do you always work with concrete values, or maybe you consider some quantified values in your approach somehow? I mean, for instance, for some price for any worker or something like that.
So, did
you generate some test cases in this case or not?
Did I use this algorithm in real cases?
Okay. We will have dinner and you will have enough time to discuss this issue. Let's thank speaker again. So the last speaker of the first afternoon session is Vladimir Agafonov, correct?
Correct.
He will present joint research with Pavel Frolov and Alexei Meshkov, an approach to test program generation for memory coherence verification of Elbrus microprocessors. Correct?
Okay, correct. Hello, the audience. Let's start from consideration of memory subsystem of microprocessor Elbrus 16C. This microprocessor designed by MCST and consists of 16 general purpose cores of Elbrus architecture version 6. Each core includes 2 levels of private cache memory and memory access unit that provides memory ordering and loads gluing mechanism. This processor also has 4 home memory units to access to DRAM and 8 memory controllers, support DDR4 memory standard. Up to 4 microprocessors can be combined into a single system with coherent memory. So microprocessor consists of many hardware units, and during the development of these units, errors may be made, so the verification is necessary. Elbrus is a very long instruction board architecture. Each leaf contains up to 6 instruction channels, and in each leaf can be placed up to 4 memory access instructions with some restrictions. The aim of the work is to develop a pseudo-random assembly test generator for verifying the memory coherence of Elbrus microprocessors. Test generator requirements are self-checking test generation for verifying on FTL simulation and on the Fpga-based prototype. Second requirement is flexible configuration of generation parameters using scenario files. The next functionality is need to be verified. Memory access of various types, memory coherence mechanisms, functioning of individual cache memories, leaf execution, stored load bypasses, and gluing of load accesses with the same address. So the test should contain memory access instructions with various parameters, creation of multiple cores with shared memory, sequences of memory access instructions at addresses leading to resolution of cache lines, leaves with multiple memory access instructions, and sequences of memory access instructions with the same address. In Elbrus architecture, memory access type is defined by instruction type. It can be loaded or stored by format and by memory address specifier or MES. MES defines the operation functionality, the data placement mode in different levels of cache, and the memory type. Supported operation functionality, data placement modes, and memory types are presented on the slide. General cacheable and general non-cacheable are coherent memory types, while external configuration are incoherent memory type. Now, let's introduce the term set of memory access types defined as follows. Set of memory access types is a subset of sets of product of sets of memory access instruction types, formats, and masks. So algorithm of memory access instruction generation looks like first address choice, next generation of memory address type belongs to a set of memory access types for the chosen address, generation of rate mask only for masked store instructions, and register choice. Special structure memory map was developed to describe for memory accesses. This structure matches each memory fragment with the following parameter set. Set of types, formats, and massive memory access instructions. The core owner. Core owner is a core that can access to the described memory fragment. Stored load ratio and use of priority. Memory fragments cannot overlap. To activate coherence mechanism, it's necessary to organize operating of several cores with shared data. The shared memory. There are 2 approaches to organize memory sharing. There are true sharing and false sharing. True sharing is the operation of several cores with overlapping memory fragments. Such approach allows using coherence mechanisms, but requires providing certain order of memory accesses to a memory fragment. This is high costed because need usage of core synchronization procedures. Another approach is a fault sharing, is the operation of cores with non-overlapping memory fragments of the same cache line. Such approach allows coherence verification. Determinism is provided. We don't need any synchronization procedures, but the number of checking situations is decreasing. It was decided to mainly organize memory sharing by fault sharing approach, but at the same time support true sharing at some extent. So as a result, we develop next test structure. Firstly, a system initialization program is executed. This program configurates system under test and allows to configure units of memory subsystem with non-default setting. After that, the sequence is executed in a loop with parameterized number of iterations. And finally, test ends with printing exit code and executing stop procedure. The sequence consists of initialization procedure of using memory and registers, and parameterized number of sections and self-checking code. Each section includes synchronization procedure and sequence of memory access instructions that implements memory sharing by fault sharing approach. Each test section is based on different memory maps. So when in transition between sections, true sharing may occur. Furthermore, some cache line may change their memory type from coherent to incoherent in transition between test sections. So such cache lines must be flushed. So as bonus, we have cache line flush verification. Cyclic execution of the sequence allows to achieve various test execution dynamics, especially on prototype. Now let's consider leaf generation and test sequence section. Algorithm starts with scheduled instruction choice to insertion in the current leaf. Initially, no instruction is scheduled. Random weight generation occurs with specified probability. If no random weight instruction was generated, memory access instruction is generated by memory map. The choice of the memory fragment and the instruction type is performed randomly according to the specified distribution of priorities of use and slot load ratio. After that, searching for free channels in the leaf is performed. If no free channels found, new leaf will be created, else will be used currently. After that, random generation of allowed instruction and leaf channel choice is performed, and generated instruction is placed into the leaf. Finally, another memory access instruction can be scheduled for insertion in one of the next leaves. Such approach allows to generate sequences of instructions with a specific memory fragment and helps to verify store to load bypasses and loads gluing. For the convenience, the user is given opportunity to describe memory areas at the more general level. Description is made for arbitrary memory areas. Corresponding to each memory area, the following set is placed, where C is a set of allowed core owners and S is a set of allowed size memory fragments. Algorithm of memory map formation consists of several steps. Splitting of the memory area set into fragments corresponding to cache lines with the parameter set inheritance. After that, correcting mass set for each cache line fragment, because operating with the cache line should be performed either by coherent or non-coherent accesses. Next, splitting cache line fragments into fragments of allowed sizes in a random way. And finally, mapping map parameter set with random coroner to each resulting memory fragment. For the convenience of format a set of memory areas aimed at created evictions in the specified level of cache, memory areas generator is implemented. Input parameters are description of addressing the target cache and the number of cache lines. As a result, we have a set of memory areas that corresponds to a given number of cache lines of the target cache level with the same indexes and different tags. Self-checking. A ready-made tool is used to generate the self-check code, self-check gen. This tool provides code generation for comparing register values with reference values. So checking data in memory should be read into registers. The source of the reference values is the functional model of this verified system. Initially, the generator was simpler, but during the process of use, some improvements was made. There are multiple sections support, L1D scenarios, address generation for L1D and high memory support, multiprocessor system support, and random L3 configuration, 48-bit physical address support, cycles, and wait instruction generation. Now let's move on to statistics on detected logical errors. Verification was carried out by running the generated tests on RTL simulation and on FPGA-based prototype. Failed tests are saved into regression base and regularly run for rapid detection of regression. Total of 77 logical errors were found, 59 of them during RTL simulation, 9 during runs at prototype, and 9 during regression-based runs. It can be seen the generated improvements lead to peaks in error detection. The same statistics only by units. It can be seen that multiple sections, L1D scenarios, address generation for L1D, and high memory usage lead to peak on errors detection in L1, translation to the side buffer, memory access unit, home memory unit, memory controller, and L3. Multiprocessor system supports and random L3 configuration allow to detect errors on chip network, L3, and memory controller. 48-bit physical address support allows detect errors in L1, memory access unit, home memory unit, and memory controller. Cycles crash at L2 on prototype, and wait allows to detect errors in translation to the side buffer and in L2. On the slide, detailed statistics on detected errors are presented. It can be seen that 19 errors was found in L1 cache, 10 in L2, 10 in L3, 5 in translation local-side buffer, 13 in memory access unit, 4 in on-chip network, 6 in home memory unit, 6 in memory controller, and 1 in diffuse controller. Some errors were found only on prototype due to diverse execution dynamics and large number of test sequence iteration. Errors were specific only for prototype. It was bad wires and timing problems. That's all. Now it's time for questions.
Thank you very much. Questions, please.
If possible, could you define very clear research problem in your work? So I understood a lot of interesting engineering work, but what is the research point?
Research is a development of test generator for verification of memory coherence of Elbrus microprocessors. Research is a development of methods that can be used for verification. Okay, method for instruction generation, methods of describing memory accesses, method of organizing shared memory.
You presented that you found a number of errors, and the question, how many errors are remaining in the code? Do you have some measure? What are the coverage of your tests, or some other means to assure that there are less, how many errors still exist?
Okay, we don't support garbage collection, unfortunately. Maybe it will be supported in future, but it's quite big amount of errors.
You talked about garbage collection, but in memory subsystem, how many errors still exist?
We don't know how many still exist.
Do you measure coverage somehow?
Fortunately, we can't measure coverage at the moment. It's not supported.
Very user question. Did you fixed these errors before production of processor, or they still exist?
Okay, verification
Best
is
question of today.
a part of process of develop of microprocessor. So the errors should be found during the development and should be during design and fixed.
Of this question, we will compare. I was impressed by the number of errors, about 50. So some detalization of this question. What was, where was errors found? It was some very draft design before rigorous testing, etc., or it is was already ready to product during previous technology, and you additionally have found 50 errors.
70. Okay, verification was produced during the whole time of designing microprocessor. Yes, inside. Yes.
I also would like to ask a question. Maybe I miss it in your talk. What is the reason? What is the cause why prototype had less errors than final prototype?
This is because prototype is not so frequent available.
Was it fully functional?
Yes, of course. But we can't use it frequently, only episodically.
So the reason is simply it was not tested well, perhaps.
Maybe yes.
Maybe. Okay. Any other question, please? If no, sorry.
So I have several questions. One of them is, how do you get information from FPGA prototype? So technically.
Okay. There are procedures and aperture that allows to print some information. So test can print any information. For example, error code, or maybe some other information that can be useful to analyze the error. And also there are some JTAG and logic analyzers.
So do you use JTAG and logical analyzers also?
I don't use, but engineers use.
Yeah, and one more question is, how do you handle non-determinism execution issues? So do you use false sharing only?
No, true sharing is also used, but only between these sections. each section includes synchronization procedures, so there aren't any non-deterministic moments.
Okay, thank you.
Any other question? If no more questions, let's thank speaker again.
Thank you.
And my duties are over, and I should pass turn to Sergei Smolov.
To me, I guess. No. I think I prefer this place for moderation, for convenience. Yes, thank you so much. We are starting very short section, I guess. It is called Application-Specific Methods and Tools. And first talk is Wi-Fi Sensing Human Detection with Kolmogorov-Wiener Filter and Gated Recurrent Neural Networks. Speaker is Pavel Shibaev. Is Pavel here? Oh, okay. Please.
So, like, hello, my name is Pavel Shibaev. I'm the bachelor student of Moscow State University, Faculty of Computational Mathematics and Cybernetics. My research covers Wi-Fi sensing, human detection with Kolmogorov-Wiener filter and gated recurrent unit neural networks. So basically, what is Wi-Fi sensing? So like literally nobody might have heard about this. So like I suppose everybody understands that Wi-Fi access point, or like as it is usually referred to in Russia, like Wi-Fi router, is a radio transmitting device. So it's capable of transmitting and receiving the radio signals, and that is why like we are able to use it theoretically as a radio locator. Like we have different frequency bands for radio location, and the frequency bands that we have reserved for the Wi-Fi signals, they are about the same. We have with the so-called battlefield recognition systems. But I'll be using the approach based on the received signal strength indicator, and it turns out that a human is quite distinguishable from the surroundings, like as you can see from this table. So what is RSSI? RSSI is a physical measurement that represents the power present in the signal. So when the man or a human passes between two Wi-Fi devices, the RSSI quality drops. You can see like RSSI in every like mobile phone or on your laptops. There is no common formula to calculate the RSSI. Like it is determined by the Wi-Fi devices manufacturers. Here is some reference formula. Like D is for distance from transmitter to receiver. D O is distance to control point. PO is control RSSI value on the distance. DO N is absorption rate that is common for like the medium through which the signal is transmitted, and PD is like the calculated value. This value is measured in decibels per milliwatt, or like commonly written dBm. So mathematically, we're able to extract RSSI values every a second. So there is a vector of RSSI values, discrete values, and for each moment of time, we have labels. Like 0 represents if the moment, the fact that there was a human between the Wi-Fi access point. 1 represents that there was human, and 0 represents the absence of a human, and the goal is to find an algorithm to identify the human presence. There are like 2 approaches. One is statistical, like remove the noises that were not caused by the human presence. For example, these noises can be caused by humidity or temperature changes. Or another approach is based on machine learning. We just set up the supervised learning pipeline and get the results on the unlabeled data. Here is like some review of the algorithms that were tested for our problem on the RSSI data. So important things to notice is the algorithm class. Like I've noted, said it can be some statistical thing like Markov random fields, or a combination of some means, or a Kalman filter, which appear to be one of the most efficient approaches, or it can be like ML-based approach, for example, k-means. Denoising is also essential. It can be done explicitly or implicitly by the algorithm without some special procedures. We have chosen the accuracy score to be our key metric, like it was present in all the papers. That is why we just inherited that. Hardware is also important, like in different research papers. There are different hardware is used. We use just simple Wi-Fi APIs, and like great accuracy was actually reached, but on a special hardware. And also the venue is also very important. And we decided to try out 2 new novel approaches. One of them is Kolmogorov-Wiener filter, which is a simple counterpart of Kalman filter, and try to set up something sophisticated like the gated recurrent unit network. So the chosen approach and experimental setup is the following. So we like have 2 access points, and the human is passing through them while present in the room, and then the human goes out, and the RSSI data is transmitted to the laptop. We're using the Kolmogorov-Wiener filter to filter out to remove the noise, and after that, to determine the outliers associated with the human presence. Also, we compare our approach with the well-known algorithm with additional pre-processing with sliding window technique. The considered algorithms are tree-based algorithms like gradient boosting, AdaBoost, and random forest, and logistic regression. Here is the architecture of the gated recurrent unit network. It's pretty simple, like 1 Kirill layer and 2 dense layers. Models comparison, like in the living room setting, in the office room, training on the living room, and then testing the algorithm in the office room, training in the office room, and then testing in the living room. So the conclusion is the following. So although it was quite simple to implement the Kolmogorov-Wiener filter, it turned out that it's not like portable. So here we can see that the accuracy score and TPR, like a true positive rate and TNR, might be quite low for this filter. Machine learning approaches are by far like the best, but at this point, as it is research in progress, I have not figured out how to beat the classic ML approaches like logistic regression. So like on all the tables I have highlighted with the bolts, like either gradient boosting or logistic regression wins. The further work can be done with CSI, so channel state information. Also, like a publicly available data set for the industry is needed. And maybe we can consider combining like collect data from several access points. Yeah. Thank you for the attention. Questions are welcome.
Thank you very much for clearing up your approach. And I want to ask you if what are the benefits of your approach in the comparison of well-known ways to find someone's body in the living room? For example, infrared devices that are much cheaper than buying a router or some laptop to analyze the data about the different measurements like that.
So yeah, thank you for your question. There is like an ongoing debate. Like IEEE is now heading for the Wi-Fi 7 standards, which I have mentioned in my paper, but unfortunately not in my presentation. And there is a working group that considers like to add support for Wi-Fi sensing to the new upcoming Wi-Fi standards. And why Wi-Fi is why this is great is that like a Wi-Fi is going to be a part of essential like IoT setting for every house out there, every smart house, and you do not actually need any additional infrastructure like feed sensors or infrastructure infrared sensors to install. You just install like a Wi-Fi system in your house, and with that you get not only access to the internet but also, for example, alarm system.
I also have some user question again. I am a bit misunderstood. You said at the beginning and didn't clarify it that it is necessary to detect some people, but what is the purpose of this detection? Maybe to reduce the influence of radio beams, or maybe to understand that people come to the room and switch on the lights, and what purpose?
Oh, like as I've thank you for your question. There can be several approaches. One and most obvious is to detect, for example, robbers in your house or thieves. Another one is for business to monitor the density or the crowd in the shopping malls, for example. If we go further, like with the improvement of the quality of Wi-Fi antennas, like there are more and more cells, and we can get more information on the radio signal, and with that we can go even up to like gesture recognition. There are even such works.
More questions, please.
Are there similar work, other work in the world? If it is possible, the idea looks so natural that some would expect that some startup already implements this idea. Or no? What are principal difficulties which you overcome? So I suppose maybe but others did not overcome.
So I suppose, like from this point of view, like from maybe business point of view, where like on the very beginning, I mean, actually now people, RSSI is not like something that is really novel. Like RSSI have been used for years for different purposes. Now the majority of people are working with channel state information. There is like some additional information about the Wi-Fi signal you can get from the Wi-Fi hardware. The problem is that Wi-Fi hardware now is like commercial. It's firmware, and it's like impossible to collect this information like easily. And the startups that there are like do actually some Wi-Fi sensing startups, they do that, but they do very complex engineering to collect this data, and currently I'm not capable of that. So I hope that with the new standards we will get more exposure to data.
More questions, please.
I would like to ask about the thematical part of your talk. Why Kolmogorov-Wiener filter? Why any other? What alternatives or options do you consider?
So like I've seen the Kalman filter performance, and it was like by far one of the best, like 95% accuracy. And like I thought, what are the alternatives? And like the majority of the textbooks on the signal processing, they say like the Kalman filter replaced the Kolmogorov-Wiener filter for some signal processing methods, and I just decided to consider it because it wasn't considered before.
Okay, thank you again.
Thank you very much.
Next talk is called Handwritten Signature Verification Service. Speaker is Sofia Vdovkina. Is Sofia here? Or maybe a co-author? No? No. Well, I think now we have coffee break till 16:30, and after that we will have tutorial. Such a mystical story. Well, I'll switch into Russian. София Вдовкина или Сергей Шибанов из Пензы? Нет, никого из них. Может быть, они у нас в Зуме, кстати. Интересно. Нет, в Зуме их нет. Ну, по всей видимости, доклад не состоится. Кофе брейк.